Good morning, everyone. Looks like today we're going to be looking at homework number 8, lecture 10 in lab 10. Wow, this marker really kicks the bucket, huh? Unless this is homework 8, lecture 10, lab 10. Nope. I think I must have left the cap off this guy. That's just not good. Just let me turn the lights up, guys, and open up a new marker. Fresh one. Could you guys call up the questions and get the numbers for me? Should be chapter 9, I believe.
That's number 48.
Okay, actually, Megan, hold on. Let me clean this.
Yeah.
Should have done that this week. Okay, and chapter 9, read them all the numbers out to me so I can put them up here.
48, 55, 57, 59, and 60.
Excellent. All right. Why don't you do us the honor? Wait a minute. Let me go into full screen here. Close. Full screen on me. Okay. Oh, let me get rid of that glare on the window. Okay. Chapter 9, number 48. What happens?
Okay, so miniature Mars. Suppose Mars had turned out to be significantly smaller than its current size, say the size of our moon. How would this have affected the number of geological features due to each of the 4 major geological processes? Do you think Mars would be a better or worse candidate for harboring extraterrestrial life? Summarize answers in 2 to 3 paragraphs.
What are the 4 geological processes? Let's remember what they are first.
Those are impact cratering, volcanism, plate tectonics, which is unique to Earth, and erosion.
We didn't talk as much about these things themselves. We'll do that a little bit today, but these are the 4 geological processes. I wonder how making a planet smaller would affect its geological activity. This is something we sort of danced around but didn't quite cover. Does anyone remember what determines how much geology? I may have actually had that as a note now that I think about it. Something to do with, wow, why is this thing so messed up? Slide 24, slide 25. Huh. I left this open all weekend. So, geez Louise. Let's see if I can open it again if it likes me more this time. Okay, that seems to have fixed things. Slide 21 is what I wanted. This slide has something to do with the answer to our question. What's going to determine there are fundamental properties that control the amount of geology a planet has. And according to this, one of our indications for geology is how warm the interior of the planet is. Which of these planets have warm interiors and which of them have cool interiors? Do you guys know the answer to that question?
Isn't it the terrestrial planets have warm interiors, or?
No, we are in a domain still where we have just been talking about the terrestrial planets. We haven't even gotten into the Jovians. That's a whole different bag of crazy. But within the terrestrials themselves, within this zone, some of these planets are geologically active and some of them are geologically dead. But perhaps we didn't get far enough along for you guys to know which are which. We're talking about the role that size has on a planet.
Wasn't it the lithosphere?
Yeah, something about the lithosphere. What's
the thick lithosphere is the cold interior, and the thin lithosphere has the warm interior in active geology.
So these guys are your cold planets, right? And these ones are your hot planets. And hot on the inside, I mean, not on the outside. This is interior heat. And you can tell these planets are cold because their lithospheres penetrate down deep into their interiors. The lithosphere is the frozen outer layer of the planet, whereas these planets comparatively have thin lithospheres relative to their interiors. So Mars is a planet that's somewhere in the middle, but is today cold. We're asking, what would it have been like if we shrank it to the size of Mars? If we shrank Mars to the size of the moon? Now, when we look at this, one of our lab today is going to be to analyze the surface of Mars. And we can do that with this topographical map called the Mars Mola map. It'll actually be in your labs, excuse me, in your lab today on the surface of Mars. But let's just call up that Mars topographical map. This one has been color-coded. It doesn't reflect the red surface of Mars, but the colors are being used to show elevations. But what you can see is that Mars has diverse types of geology on its surface. Mars has some of the largest volcanoes in the entire solar system, although they seem to be dead today and not active. It has a giant supersized version of the Grand Canyon called the Valles Marineris, named after the Mariner spacecraft that first visited it. It has cratering like the moon. It has stuff that looks like dried up riverbeds going into a massive, kind of looks like almost like there's an ocean here or something. It has all kinds of interesting geological features. Things that look kind of like the lunar maria, these planetias. The moon does not have this diverse level of geology. We don't see volcanoes, or we don't see giant shield volcanoes on the moon anyways. We don't see giant massive chasms and dried up riverbeds. We do see craters though. They both have some craters. Another thing this question has to do with is about the way that planets heat up and cool down. At the end of our lecture last time, we learned that planets start off hot but cool over time, but they can continue to generate heat through processes like differentiation, where friction sucks the heavy metals down to the core, and by radioactivity. But meanwhile, they're fighting the thermal death of the planet as infrared radiation shines away light into space over time. I wonder if it's better to be a big planet or a cool planet in terms of heat retention. What do you think? Should big planets stay hot longer, or should cold, little tiny planets stay hot longer?
Would it be little planets because they have less to like heat up kind of, or to keep warm?
So this is going to be explained in a question that we do after this one, in question 55. But it is confusing, Olivia, because there are two sides to it. When a planet is big, it has more volume, and more volume usually means you can hold more interior heat. But the problem is that bigger planets also have more surface area, and more surface area means you can shine away your light. So I didn't love the way you said it, because the smaller planets will have less reservoir to hold heat, but they do also have less surface area to shine away. However, the volume of a sphere grows as the cube of the radius, whereas the surface area of a sphere grows as the square of the radius. So pound for pound, as a planet gets bigger, its volume grows more quickly than its surface area does. And this tends to mean the opposite, Olivia. It tends to mean that the bigger planets stay hot longer than the small planets do. And that's really what this planet what this question is talking about. They're imagining if we made Mars smaller, the size of the moon, what's going to happen to its interior heat, and how would that affect the number of cool surface features that we see on it today? So let's just do some guessing. Let's leave cratering aside for a second, and let's start with volcanoes. Do we think a cooler, smaller Mars would have more or fewer volcanoes?
Fewer.
Yeah. And as we'll see in today's lecture, thin lithospheres are a requirement for volcanoes. And that's just because of the nature of what a volcano is. It forms initially from vents or cracks in the lithosphere that allow warm layers of rock to push their way up out onto the surface. And if the lithosphere is too thick, it will be impossible to form those cracks and vents necessary for the interior heat to ooze its way out. Also, there won't be much heat to ooze its way out. The rock will be kind of solidified and frozen solid. It won't be convective. So we'll expect fewer volcanoes. Tectonics will also require a thin lithosphere, so we'd expect those to drop. Erosion usually takes the form of wind, water, and ice. Now, it turns out that volcanoes are related to planetary atmospheres, because planets tend to get their atmospheric gas from volcanic outgassing. So, in a way, atmospheres contribute to erosion because you need air, or you need some kind of atmosphere to have wind. And water requires surface pressure. You can't have water in the vacuum of space. you could have ice, but it's debatable how much transport that ice would be getting. Well, I suppose ice can transport across surfaces without an atmosphere, but it's a little bit more difficult. You either tend to be a vapor or you tend to be frozen in place. So that would probably mean without an atmosphere, erosion wouldn't be possible either. Impact cratering, on the other hand, that's something that you would continue to expect to see, because if you think about the moon today, the moon is covered with impact craters. There's no atmosphere, there's a surface, and there's plenty of rocks in space floating around waiting to hit it. Let's see if we can sum all that up in a paragraph together, okay? So if Mars had formed smaller, say the size of our moon, we would expect its surface features to differ significantly from the ones we see today. A smaller Mars would have lost its internal heat much quicker let's say much earlier in the solar system's history, resulting in a thick lithosphere incapable of forming vents or fractures. This would have prevented the epic shield volcanoes of Mars from forming. We'll say tectonic features such as the Valles Marineris I'm gonna have to continue up here. Tectonic features, oh, sorry, I didn't realize you guys couldn't see that. Tectonic features such as the Valles Marineris would also not easily form from a thick lithosphere. Now we'll get on to the erosion bits. Without volcanic outgassing, these are the terms that people use for the gas that comes from volcanoes. They say it's volcanic outgassing. Mars would not have formed the thin atmosphere it has today. Leading to a loss of wind and water erosion that carved out river valleys. I'm just going to erase a few extra lines here. That carved out its river valleys. IES sounds right. The only geological forces left would be impact craters. Which would continue to rain down on the surface. Probably shouldn't use the term rain, since that, we'll put it in quotes like professors like to do. Actually, we'll put rain down in quotes. Rain down on the surface from space. In short, and I guess this wasn't really that short, but in short, a smaller Mars would resemble the moon, a cratered airless rock incapable of supporting life. Woo! Those word questions are a real doozy if you want to do them right. I want to point out that what we did in this question is not only talk about the underlying forces, such as the loss of internal heat and the thickening of the lithosphere, but you'll notice that I also pointed to specific examples on the planet when possible, like for instance, mentioning that water erosion carves out its river valleys. Being able to include these specific details in your answer really gives it gravitas. And these are things to think about when you write essays for your other courses as well, to include specific examples because they add weight to your argument. I'm going to heat up a cup of Joe while you guys finish your copying. All right. Have we all finished?
Not yet.
Oh, okay. Who is that? Who's talking to me?
Sorry, I'm a slow writer.
That's okay. I'm a slow coffee maker. By the way, for everyone else while waiting, a couple of interesting space news events this week. Speaking of Mars, NASA launched its Perseverance mission this week. And Perseverance is the next super rover that's going to travel to the surface of Mars and explore one of the craters that we believe may have had liquid water in it in the past. This mission is definitely having as one of its primary science objectives the search for any kind of organic materials or cellular fossil record that could have been evidence of life forming outside of our own solar system. So that always brings with it the exciting possibility that in our lifetimes we might discover life outside of Earth, which would be really cool. The other big news was yesterday, the two astronauts that were flying aboard the SpaceX Dragon capsule safely returned to Earth and landed in the Gulf of Mexico. So I watched that touchdown live yesterday, and that was kind of cool. Okay, Adrian, you all set? All right. Let's try chapter 955. Adrian, are you down to read that?
Sorry, the phone's going off. Yeah, it's a great time.
I just can't believe anyone still has an old landline, that's all.
Yeah, we still have an old landline. Surface area to volume ratio.
Okay, actually, for the future, we're gonna change it to volume to surface area ratio. I'll explain that in a minute.
Okay. Compare the surface area to volume ratios of A, the Moon and Mars, and B, Earth and Venus. In each case, use your answer to discuss differences in the internal heat of the two worlds.
Okay, so let's start off by doing a little description of what I was talking about before. Here's a circular planet, okay? Let me see if I can do that circle a little better. A spherical planet, rather, has a radius r. And we tend to know some things about spheres. Spheres have a volume, which is known in geometry to be 4/3 pi r cubed. The surface area of a sphere is also well known from geometry to be 4 pi r squared. And these are just facts. It is known, okay? Now, in some ways, because planets start off by contracting over a great physical distance, they release tons of gravitational potential energy. And this means the internal heat of a planet starts off very high when they first form, and it continues to be nourished by differentiation and the radioactive materials that are spread all throughout its surface, volume. Because the radioactive decay is happening all throughout the interior sphere of Earth, the volume of a sphere, the volume of a planet tends to sort of be proportional to the amount of internal heat that it can hold. It's just a bigger reservoir, you know? On the other hand, planets are constantly shining away their light into space from infrared radiation. And because of this infrared radiation shines from the surface rock of the planet, it tends to be that the amount of surface area that a planet has is proportional to its cooling rate. Now, I'm not sure why, but someone at some point came up with the concept of surface area to volume ratio, which is supposed to be an indicator of how quickly a planet cools down. I find the surface area to volume ratio to be extremely awkward and confusing for students because it puts the radius in the denominator of the equation. I think a much more logical approach is to consider the volume to surface area ratio of a planet. And if we plug these two formulas in, 4 pi r cubed, well, let's make it 4/3 pi r cubed over 4 pi r squared. Can any of you algebra whizzes tell me what that's going to reduce to? What do I reduce that to if I cancel out common factors in terms? Or I guess common factors is probably the better way to say it.
Well, wouldn't pi be canceled out, and then radius would just be r, like r to the first, if you will.
Sure.
And then the fraction one, I don't know that one.
Well, this is the top of the top, this is the top of the bottom, right? Okay, so what's my final answer, Megan? Yes, you're right so far. Keep going, though. You're not done.
1/4 r.
What about this 4? Did that disappear?
No.
What
but
about this 3?
No, but I multiplied by the inverse of 4/1.
No. If you're going to do something to the top, you have to do it to the bottom as well. What does 4/3 over 4 reduce to? Can you not handle that? Remember we played that game earlier where we learned how to cancel out common fractions? This is the top of the top. Where does the top of the top go to? Do you know what I'm talking about, Megan? I am talking to Megan, right?
Yeah. I'm sorry, what do you mean?
I think you should go back to chapter 4 where I taught you how to deal with fractions within fractions. 3 out of 2 people are bad at fractions, okay? So I need you to go, we played a little game that went like this. A over B divided by C over D, and we reduced it to a single fraction, right? You probably have no idea what I'm talking about.
No, I do. I just, fractions confuse me. If anyone else.
Yeah, does anyone want to help Megan out here?
It's 1/3.
Yeah. So the top of the top fraction ends up on the top. The bottom of the top goes to the bottom. The top of the bottom stays on the bottom. The 4's cancel as well. So what's my final result?
1/3 r.
Yes. This means something for those of you who don't speak math. The volume is kind of like the amount of internal heat a planet can hold. The surface area is the cooling rate. So the volume to surface area ratio in a way, is kind of proportional to the amount of internal heat a planet will retain over time, because it's the heating to cooling ratio. Since this number is bigger with larger radius planets, we have the important result that bigger planets stay hotter longer. Bigger planets stay hotter longer. I don't know about grammar, but there's an idea there. And that should be a common result. I mean, suppose you baked a potato and a turkey for the same amount of time in an oven. If you took them out of the oven and put them down on the windowsill to cool off, which one would you expect to cool faster, the turkey or the potato? I hope you know the answer to that question.
Potato?
Yeah, because it doesn't have the same thermal reservoir. It's gonna just shine away its light faster. And that's what planets do. Mars, or, well, in this case, what part A, Adrian, what were we supposed to compare? Was it Mars and the moon?
The moon and Mars and Earth and Venus.
Okay. So Mars has a radius of 3,400 kilometers. I can help out the class there because I know some stats. Versus the moon, whose radius is 1,700 kilometers. So here's how we'll set it up. We'll set up the volume to surface area ratio for Mars, and we'll divide it by the volume to surface area ratio for the moon. The 1/3 will cancel out. Then we have 3,400 kilometers divided by 1,700 kilometers. What's that give us, students? What'd you get, Tim?
2.
And do you know what the 2 means?
The 2 means that the moon cools off twice as fast.
Yeah. That's one way to put it. The moon cools off twice as fast. Tim, I'm going to take a slightly different way of saying the same thing. Since I've got heating on top and cooling on bottom, I'm going to say Mars will retain twice as much internal heat as the moon. Although what you said was essentially the same thing. They wanted us to do it your way, the surface area to volume ratio, but I'm going to say Mars will hold twice as much internal heat as the moon.
Does this stuff factor into entropy?
Well, this is about entropy, right? The leaking of energy from the interior of a planet to the exterior of a planet is a manifestation of the second law of thermodynamics. The fact that energy wants to spread itself out into as many states as possible and wants to disperse itself as evenly as possible throughout the universe. So in the same way that ice cubes tend to melt in water over time because they don't like to keep the heat out of their little cubic interiors, planets also don't like to become reservoirs for heat in space. That heat tends to distribute itself out over time. So this is a manifestation of entropy. And if you guys want to read about entropy at a deeper level, there's a really cool website where a person tries to describe entropy is something that you can describe in layman's terms, and then there's like a deep level, a physics level of understanding entropy, which is really cool. And this one guy wrote this like little website where he tried to bridge the gap. Let's see if I can find it. He makes this analogy between entropy and counting sheep, which I thought was pretty sophisticated, and I enjoyed it. It was like a, you know, you read it while you eat your Cheerios in the morning kind of thing. And let's see if I can find that and share it with you. Entropy counting sheep. Yeah, this is it. Entropy explained with sheep, okay? So why does this GIF look totally normal? You see an ice cube melt into a glass, but this one looks strange. Ice cubes don't tend to spontaneously form from water, right? And that's because energy doesn't like to be unevenly distributed throughout a situation. Hold on. The bill collectors are back. Okay, let's mute that. Okay, so this guy tries to get into the one-way direction of entropy with this really cute arrangement of counting sheep, and it's interactive. You can say, oh, there's 10 different ways that the sheep can be dragged into these different boxes. Why don't you try to find all the different configurations? And once you find them all, they give you a congratulations. And they try to explain why, oh, I found 7 out of 10 arrangements. I can do this. I found 8 out of 10, 9 out of 10. Which one am I missing? Anyways, the sheep here become symbolic representations of the energy states that particles like electrons and atoms can take. And then they imagine sort of creating situations with lots of particles and lots of boxes, and they show you the different ways that you can arrange atoms in space. Look, I don't have time to get into the whole thing. Entropy is another lecture all unto itself. All I know is that website is really cool, and boom, let me share it to everyone in the meeting. I challenge you to read that in your free time. Just call the link up on your phone sometime and read it for kicks. It's pretty cool. All right, let's try to do Earth and the Moon. Sorry, Earth and Venus. So for part B, we have Earth, which you may remember has a radius of 6,400 kilometers, versus Venus, our so-called sister planet, with a radius of 6,050 kilometers. Okay, so we'll divide the radius, oh, sorry. The volume to surface area ratio, hold on, this isn't going very well. Volume to surface area ratio for Earth divided by the volume to surface area ratio for Venus. We'll skip the 1/3 this time. We'll go as 6,400 kilometers over 6,050 kilometers. And that's approximately equal to
1.
Yeah. The meaning of which is that Earth and Venus hold similar amounts of internal heat. Both Earth and Venus have atmospheres and many volcanoes. One of the strange mysteries we ought to clear up today or tomorrow is that Earth has a robust set of plate tectonics, but Venus does not. And that's very interesting to think about since both planets presumably have equally thin lithospheres. Earth's lithosphere is capable of forming large-scale cracks in tectonic plates, but Venus is not able to do so for some reason.
Is that because we have different cores or because of the moon?
It has neither to do with our core nor the moon. Earth's moon does not have a significant effect on our internal gravity. Its tidal forces aren't great enough. And as you can see in the slideshow here, although that's a reasonable guess, but it turns out to not be the moon, at least as far as I know, the cores of Earth and Venus are identical. They are both made of nickel-iron mixtures with silicate rock on the outside. I wonder what else it could be. What does Earth have that Venus doesn't? And, you know, part of this will be our lecture today, Tim. I should talk a little bit about tectonic plates, but if you want to know where the boundaries of Earth's tectonic plates are, you have to follow the earthquakes. And this is a picture that I'll show in today's lecture of the location of where earthquakes are predominantly found on Earth. Each green dot represents a recorded earthquake in the last 100 years. And they perfectly trace out the boundaries of our tectonic plates. These are these fractured lithosphere chunks that float around on the underlying mantle. Now, they are not randomly distributed around Earth, although they seem to be at first. All of these boundaries have one thing in common.
Liquid water.
That's right. If you think about it, Tim, water serves to lubricate rock and help it to crack and fracture. Just think about the Grand Canyon getting carved out by the Colorado River. If water can do that to the Colorado River, it can certainly help form these cracks in our lithosphere. Now, if you look at the surface of Venus and compare it to the surface of Earth, this is part of today's lecture, of course. Let me show you two side-by-side views. I shouldn't really spoil the surprise here, but I'm doing it anyways. This is a grayscale or tan scale, I guess, topographical image of the surface of Venus. Compare it to a similar topographical image, tan scale image of the surface of Earth. So there's Earth, and there's Venus. What's the first thing you notice when you compare the surface of Earth to Venus? What's the major difference between these two pictures?
Where the water is.
Kind of, or I guess I was thinking, you can tell that this is Earth right away because of the continents, right? Which I think is another way of saying what you're saying. You're focusing on the negative space, I was focusing on the positive space. But you can see the water and you can see the continents. You see no such crazy epic continental land masses on Venus. And to me, that's a direct indication of the fact that Earth has tectonic plates and Venus does not. By the way, let's also throw in Mars in here. What's different about Mars than these two planets? Is that obvious?
The massive peaks.
Well, you're right. The volcanoes are supersized, but that's, you know, Earth has volcanoes and they're not quite as big. And Venus, all these little dots that you see all those little pimples? Those little pimples are actually pretty serious volcanoes. You're just looking at an entire surface of the planet, so they don't seem big by comparison. The volcanoes, okay, Mars's are crazy big, but they all have volcanoes. But I was thinking of another large-scale feature.
The craters?
Yeah. Mars is pitted with impact craters, coated with them. whereas Venus and Earth are relatively smooth by comparison. We'll talk about that as well today. But I don't want to spoil all my hijinks before it's time. Okay, I think we've wrapped up this question and can move on to the next one. The next one's a doozy, and it's actually about impact cratering. So that's a cool segue. So now we're going to do chapter 9, number 57. Tim, why don't you take us out for, do you have the stuff there in front of you? The questions?
I can pull it up.
Okay. While you're pulling it up, I want you guys to understand that this question that we're about to ask is not only a very difficult question, it's kind of a math doozy, but it's also about a very famous photograph taken during the Apollo landing on the moon. I don't know if it was the first one or which one exactly, but during the Apollo missions to the moon, the astronauts discovered that the moon's surface was actually coated in a fine silicate dust everywhere across the surface of the moon, known as the lunar regolith. Here's a badass picture of one of our astronauts in the lunar dune buggy there, traveling across the Maria. And you guys will notice that underneath the tire, there's a bunch of dust getting kicked up there. I'm talking about moon dust, or what's known as the lunar regolith. Can you guys see in this iconic picture of Neil Armstrong, all of the boot prints in the moon there? The entire surface of the moon is coated with a 3 to 5 centimeter layer of powdery soil. Well, soil, we can't say soil because there's no organic elements in it. It's dirt or dust. And here's a close-up image of Neil Armstrong's boot print in the lunar regolith. This is what this question is about. Consider the boot print here versus the boot prints that you'd see in the mud on Earth. If I step into a pile of mud with my boot and leave a similar impression on Earth, how long do you think it would take before that boot print got washed away or covered up with sticks and leaves? Maybe 3 days, maybe even 1 day if it rains, right? But consider that the moon has no atmosphere, and this boot print in the moon dust is touching the vacuum of space. Never a gust of wind, never a drop of rain, nothing to really disturb it at all, except for, I suppose, by the way, anyone want to guess why the moon would be covered uniformly with this fine powdery moon dust, this lunar regolith? What could be causing that? The answer is not necessarily obvious, but I just wanted to see if you could guess.
What's the question?
Why would the moon be covered in dust? Why would the entire surface of the moon?
Erosion.
But erosion requires wind or water, neither of which can be present without an atmosphere. It's another type of Megan, you had the right spirit, which is my 4 geological forces is doing this. Could you pick a different one?
Impact cratering.
That's right. See, because the moon is subject to harassment from every little pea-sized grain or microscopic pebble that strikes its surface. And the smaller the size of the rock, the more frequently they tend to hit your planet. The Earth is bombarded by objects that are smaller than a meter every hour of the day, but our atmosphere usually just burns them right up. The moon, however, is subject to not only impacts from large craters, but also micrometeorite bombardment, pea-sized grains of sand, which continually rain down on the surface and over long geological time periods grind the surface of the moon rock up into silicate dust. In fact, apparently one of the cool stories about the Apollo astronaut landing mission to the moon is they weren't expecting all this level of silicate dust. And when they got back in their capsule into the lander, the kicked up silicate dust was so intense that it was coughing them and gagging them, and they were actually worried about suffocating on bloody moon dust, just silicate moon dust, which would shred your lungs apart. So it was kind of like a tense moment of the lunar landing when they were trying to figure out how do we get all this, because they would track it in with their boots and it would kick up all around their little capsule in the lower gravity of the moon, and they were trying to clear the cabin of moon dust so they could breathe. Okay, Tim, what's the title of this problem? Sorry, I think you might be muted.
Can you hear me?
Yes.
Internal versus external heating.
Oh, is this 57?
Oh, wait. Lunar footprints.
Yes.
Assume that the moon is hit by about 25 million micrometeorite impacts each day. This number comes from observations of meteors in Earth's atmosphere, and that these impacts strike randomly around the moon's surface. Also assume that it takes about 20 such impacts to destroy a footprint. About how long would it take for one of those footprints left by the Apollo astronauts to be erased? Hints: use the moon's surface area to determine the impact rate per square centimeter and estimate the size of a footprint.
Okay, so here's the surface of the moon. We're actually going to take a different tack on it. Their method is a perfectly good method, and we're going to achieve the same results by considering probability. This could be an opportunity for you guys to get exposure to the frequentist method of probability. And here we have Neil Armstrong's boot print sitting on the surface of the moon. And we know that the moon is being struck by 25 million micrometeorite impacts per day. And we can imagine that we're playing a game of darts with a robot, and the robot is guaranteed to hit the target somewhere randomly as he throws the micrometeorite darts at the surface of the moon. Our goal is to figure out what are the chances that one of these darts will strike the footprint, and to proceed from there to calculate the amount of time it will take to destroy the foot. So let's start off by considering probability. We want to estimate the percent chance that the foot will be struck. Let's imagine a simpler version of the problem, one in where Neil Armstrong had such a gigantic foot that it covered 1/4 of the surface area of the moon. If Neil Armstrong's foot was 1/4 of the moon's surface area, what would be the probability that one of those darts would strike the foot?
1/4.
Good, or 25%. 1 part in 4. What if instead his footprint was 1/8 the surface of the moon? What would be the probability then?
1/8.
Or 12.5% chance. I guess what you're saying then, if you keep imagining dividing the footprint into smaller and smaller bits, that if you have a surface area of the entire moon, the probability of a single dart striking the footprint is proportional to the ratio of areas. The area of the foot divided by the area of the moon. So let's get a boot. Of the rubber one. For nights of cold observing at the observatory, I got me a pair, best $100 I ever spent in my life, of these Muck Boot Arctic Pro. They're pretty much like a space boot, okay? I think this thing has something like 10 layers of neoprene and is rated down to negative 60 degrees Fahrenheit. I swear to God, this boot, I can stand out in the observatory all night without my feet getting cold. And I read about them because all these Wisconsin farmers use them. They were rating the different muck boots and saying, now look, this is the boot. I can stay out in the barn all damn night long and I won't get my toes frozen. And it's a serious thing because when you're just standing out there in the cold for hours and hours on a concrete slab, your toes just freeze to death. Anyways, point being, this is the closest thing I have to a space shoe. Let's see, let's model the space shoe as something sort of like a square. We'll do length times width to get the area, okay? So as you know, area is length times width. And we're gonna do it in centimeters because that's what I've got a meter stick here. So what would you guys say is approximately the, just rough numbers here. What's the rough length of my space boot here? Guess it would help if it was right side up for you guys. What do we think?
$30.
30 centimeters? Okay. How about the width?
$11.
Okay. 11. So we have a space boot that's 11 by 30. Is that 330? I can multiply by 11. Okay. So the probability, oh, the area of the moon is 4 times pi times the radius squared. We should convert the radius of 1,700 kilometers into centimeters. So I'll do 4 times pi. I want to show you guys a little trick that I like to do. Sometimes I like to do the conversions inside the formula. So I'll do 1,700 kilometers. What's the conversion from kilometers to centimeters? Y'all remember? It's 10 to the power of 5. What you get? Punching is a U job.
Would it be 3.6 to the 19th power or times 10 to the 19th?
All right, you've made a mistake, and I know what mistake you've made.
Okay.
You typed this into your calculator wrong. Olivia, 10 to the power of 5 is 1 times 10 to the 5. But what you did is you typed 10 exp5, which is the same thing as 10 times 10 to the 5 which is 10 to the 6.
Oh, okay. That makes sense.
Therefore, you square that and your number is off by a factor of 100. So try again.
Okay.
You can actually literally go 1700 exp5 if you want. Guys, I feel like Neil Armstrong's boot print is going to be erased before you actually finish this problem.
Is it 4 times 10 to the 17?
Fine, I love it. 4, and what are the units?
Centimeters.
Try again.
Squared?
Centimeters squared. It's an area. Therefore, the probability is 330 square centimeters over 4 times 10 to the 17 square centimeters. This type of calculation, by the way, is known as a back of the envelope calculation. It usually starts off with a couple of scientists at a bar, and they've had a couple of cocktails, and one says to the other, hey, how long do you think Neil Armstrong's boot print's going to sit up on the moon there? And the guy says, I don't know, but I bet we could figure it out. And then they take out a cocktail napkin and a pen, and by the end of it, nobody wants to talk to them. Anyways, what's our probability here?
8.3 times 10 to the negative 16.
All right, and that's unitless because probabilities are unitless. The centimeter squares cancel out. That's obviously a pretty tiny, oh, I'm sorry, 16. 16, right?
That's right.
Okay. What does this tiny number mean, Tim?
Very, very, very low probability.
Yeah. I mean, which is what we'd expect. If you've got the whole moon as your dartboard and the bullseye is 300 square centimeters, it's going to be very unlikely that a single dart will hit your shoe. On the other hand, we do have a lot of darts getting thrown at the moon. What I would like to try to figure out is, well, you know, just because there are no units on this does not mean we cannot invent some dummy units to help our brain straight. The 300 centimeters squared is a different impact than the impacts covering the whole moon. Let's call the impacts that strike the foot imps, or foot impacts. And let's call the impacts that strike the moon imps, for moon impacts. If you think about it, the probability is the ratio of the number of times you'll have a foot imp to the ratio of times you'll have a moon imp. So we can invent some bogus units here. This could be considered the number of foot imps per moon imp. The 25 million impacts per day are moon imps because they cover the entire moon. The number of strikes to kill the foot is 20 foot impacts. What if I wanted to know not the number of moon impacts per day, but I instead wanted to know the number of foot impacts per day? Does anyone see how I could get that number through dimensional analysis? I've essentially created my own dummy units here. These are dummy units. since they're both impacts, they kind of cancel each other out. In other words, what I'm asking is, what should I do next?
Divide.
Divide what by what?
Foot impacts by moon impacts.
Well, we already kind of did that in a way. We divided the probability, well, we divided the area of the foot by the area of the moon under the assumption that this is proportional to the number of times the foot is hit, and that's proportional to the number of times the moon is hit.
We were doing probability of area. I'm talking about impacts themselves.
You want us to use dimensional analysis by like multiplying
Yes.
impacts by 8.3 times 10 to the negative 16th, right?
Which number do you want me to multiply then? Be very clear, Megan.
Sorry. You would want to multiply.
You're onto something.
Yeah, moon impacts in the numerator and one in the denominator, or is it flip?
Well, okay, so I like what you're saying here. Let's look at this. 8.3 times 10 to the minus 16 foot imps per moon imp. The question is, what do you want to get from this? Times something is going to give you what? These are the two numbers you got to work with. So keep going, Megan.
You're looking for moon impacts. So you'd
No.
want, no?
I know how many impacts strike the moon per day, 25 million. If I want to know how long it's going to take to destroy the foot, it might be helpful to know how many would actually hit the foot in a day. In other words, foot impacts per day. Did I lose you, or are you with me?
No, I'm with you, but like how many days would you put, like would you put days in the numerator?
Why don't you just look at the two numbers you have to work with, and what are their units?
I'm afraid I'm lost. I'm sorry.
Okay, if you put days in the numerator, what are you going to put in the bottom? You don't have a raw number of days. You have moon impacts per day. You don't know how many days it's going to take. You've got to, ultimately, you want to work with units that are tied to numbers, right? These are things that you know. I'm trying to
put 20 on the bottom.
If you did that, all right, let's talk about doing that now. This is 20 foot impacts. If you do that, Tim, you can cancel out foot impacts, but then you have a number of something per moon impact. And that's going to be very confusing. I'm not going to be sure what that means. I'd have to think about it. It means something, but I don't think that's the right way to go. I just want to see if you guys can find it for yourself, because that would be so much cooler than me telling you what to do. Once again, you have the number of moon impacts per day. Don't you think it would be more useful to know the number of foot impacts per day? This is a frequency with which the moon gets hit. I'm looking for a frequency with which the foot gets hit.
You have to figure out, you take the number of impacts per day on the moon total and divide it by the probability of it hitting that area of the blueprint.
if we divide this number by that number, our units will be foot impacts per moon impact divided by moon impacts per day. Your new units are now foot imp days per moon impact squared. Not helpful. You're getting incrementally closer to the correct answer here. Might a different approach work? Is there some way we could flip this around?
Would you flip around the 8.3 times 10 to the negative 16?
Oh God. Okay, we could. Or
No.
you could, yes, you could actually do that. Well, here's what I was thinking, guys. What I wanted you to say is, I wanted you to do moon impact, to multiply it by moon impacts per day. If you multiply foot impacts per day by moon impacts per day, moon impacts will cancel out and you'll be left with foot impacts per day. You pretty much thought of every single fucking scenario to do except for the one correct one. Now, I don't know why. I thought it was obvious, but that's because I already see the answer. It's always obvious when you know what to do, right? Anyways, that's what I was hoping for. There are 25 million moon impacts in one day. What's that give us if we multiply? Maybe the fact that I wrote it like this is what confused you guys, because I had the division bar on the side. Maybe that threw you off. I don't know. Well, anyways, what do you get if you multiply these two numbers?
I got 2 times 10 to the negative 8 to the negative 8.
And the units are foot imps per day. Okay, I'm going to continue to kind of squeeze you guys for information here. Tim, and I'm just calling on you for fun, what do you think it means 2 times 10 to the minus 8 foot impacts per day? I mean, that's basically like saying 0.000000, 4, 5, 6, 7. That's how many foot impacts per day. So what does that mean?
That means it's going to take a lot of days to equal a full impact.
Yeah. Is there a way we could find out the number of days? Right now, I've got foot impacts per day, and that's not clay, that's day, and it's less than 1. What if I wanted to find the number of days per 1 foot impact? How would I handle that? What could I do to get the number of days per 1 foot impact? Let's think about that. I know that I get this many fractions of a foot impact in one day. What if I want to know the number of days to get a single whole foot impact?
That times x equals 1.
Yeah, and if you did that and solve for x, okay, fine, that's one way to look at it. Then what happens when you solve for 1? When you solve for x, I mean. Divide 1 by this number. Or in other words, Tim, if you just take the reciprocal of foot impacts per day is days per impact. And by the way, guys, you have a cute little reciprocal key here. You can just hit Shift and then close parentheses is 1 over x, and that will flip it. So we'll do 1 divided by 2 times 10 to the minus 8 foot imps per day. And what's that give me?
$50 million.
Yeah. 50 million days per 1 foot impact. I'm almost done. What do I have? I have 1 thing left to do.
You have to multiply it by 20 because it takes 20 to clear it out.
Good. And what's that give me?
$1 billion.
A billion days? Is that what you got?
Yep.
Okay. Let's convert that to years. One year is 365 days. Come on, Calky.
It would be 3 million years.
Not 3 million. Oh, sorry. Yes, 3 million. I apologize. I'm wrong. 3 million years. A million years from now, Neil Armstrong's boot will still be sitting there in the lunar regolith. You know, the American flag that they put down is probably already gone white from particle radiation, and ultraviolet exposure from the sun has probably disintegrated the cloth. They stuck the American flag in the moon to try to show that we claimed it, but what they probably should have done is spelled out USA in boot prints. That would have been more effective way of claiming their turf, you know. All right. I'm going to erase. Does everyone have all that? Because I need to erase. Adrian, you good? I think we're making reasonable time here. Oh, sorry. Nick, you're the next to my little Hollywood squares. You down to read?
I just gotta.
And your loudest reading voice, because your mic's a little quiet.
Which one are we on?
59.
Terraforming Mars. Some people have suggested that we might be able to engineer Mars.
Oh, wait. This is confusing. Did I assign that problem? No way did I assign that problem. Chapter 9, number 59. It should be quantitative.
Oh, yeah. Oh, hold on. I got it now. I was on chapter 10.
Oh, okay.
Internal versus external heating.
Okay.
In daylight, Earth's surface absorbs about 400 watts per square meter. Earth's internal radioactivity produces a total of 30 trillion watts that leak out through the planet's entire surface. Calculate the amount of heat from radioactive decay that flows outward through each square meter of Earth's surface. Your answer should have units of watts per square meter. Compare quantitatively to solar heating and comment on why internal heating drives geological activity.
All right, it was a little tough to hear you, but did you say how many zeros are in a trillion, Nick?
Is it 12?
Good. $400 watts per square meter in sunlight, 30 trillion watts from radioactivity. Let's draw this as a picture so we understand what's going on. Here's the Earth. We'll draw the crust or the lithosphere, whatever. And inside the planet is some internal heat due to radioactive isotopes popping off. And they're generating 30 trillion watts. That's a power or a luminosity. It's telling us the number of joules flowing out of the planet in all directions. Meanwhile, there's some sunlight coming down from space. And by the time it gets through our atmosphere, we're getting about 400 watts per square meter. What, shoot, I already got lost there, Nick. What did the question want us to do again?
Where is it? Calculate the amount of heat from radioactive decay that flows outward through each square meter of Earth's surface. And compare
Sounds to me like they want the watts per square meter flowing outward due to entropy, right?
Yeah.
This sounds like a job for the inverse square law. Because the brightness flowing at the surface of the planet will be its internal luminosity in terms of watts divided by its surface area, 4 pi r squared. The radius of Earth, 6,400 kilometers, can be quickly converted to meters by multiplying by 1,000. 6.4 million meters. Did you get me a snack? No. Oh, damn it. Okay, that's right. All right, let's calculate the brightness. So we have 30 trillion watts divided by 4 pi times 6.4 million meters squared. I'll take that number whenever you got it.
Ten times 10 to the 26th.
You forgot to divide by 4, divide by pi, and divide by the radius squared. You hit multiply. Try again.
Okay, I got 2 times 10 to the 12.
You forgot to... That's impossible. I don't know what you did. You forgot to square your radius or something.
0.058.
Yeah.
What are the units?
Great question. I was going to ask you that.
I asked you first.
That you did. That doesn't seem fair, does it? Well, what do you got in your equation here? You're calculating a brightness.
Watts per meter squared.
Yeah, we're going to compare that to the sunlight. And I want you guys to notice something. This is the amount of geothermal energy that is leaking out of Earth. By the way, Megan, we got to get your calculations under control here.
No, I got it.
Oh, okay, you did it. Never mind. What's the second part of that question, Nick? There's a follow-up thought part to the question.
Compare quantitatively to solar heating and comment on why internal heating drives geological activity.
Okay. The sun beats down 400 watts per square meter on the surface of Earth. Geothermal energy releases 0.06 watts per square meter across Earth. Which is going to have a bigger impact on the geology of Earth? Sunlight or geothermal energy?
Sunlight.
If that's the case, the planet that receives the most sunlight should have the most active geology. Mercury receives more sunlight per square meter than Earth does because it's much closer to the sun. Why doesn't Mercury have more geological activity due to sunlight then? Something's weird, Megan. This is supposed to be a surprising result. I was surprised that sunlight is so much more powerful than geothermal energy. At first, I couldn't understand why volcanism and tectonics were based off geothermal energy and not off solar energy. Until I realized, of course, that this sunlight is mostly getting either reflected or re-radiated back into space. Sunlight might heat the top meter of Earth's lithosphere, but even if you dig a hole that goes much lower than a meter, you start to realize that temperatures, well, first they drop and then they rise again as you start getting into the geothermal energy. The reason why has to do, once again, with entropy. The geothermal energy is leaking itself out of the Earth across the lithosphere. The sunlight doesn't end up penetrating to the interior of Earth, but actually gets re-radiated or scattered back into space. Even though geothermal energy is less than solar energy, it's still responsible for creating geological activity because that energy has to flow across the lithosphere. Let's explain that in a sentence. Although solar heating far exceeds geothermal energy, it's still geothermal energy that drives geology, because this energy flows outward across the lithosphere by conduction. The solar energy gets reflected back into space. I think we can squeeze this last one off if we do it real quick. Adrian, you give me a thumbs up when you're finished writing. Okay, I'm going to erase. Olivia, read me number 60, if you will.
Okay. Let me just pull it up really quick. Okay, number 60. Plate tectonics. Typical moon of one plate relative to another is 1 centimeter per year. At this rate, how long would it take for two continents 3,000 kilometers apart to collide? What are the global consequences of motion like this?
So I'm just going to imagine two hypothetical continents, okay? Wait, how do I do this? And these two hypothetical continents are separated by 3,000 kilometers. And they're spreading apart with a velocity of, did you say 1 centimeter per year?
Yes.
We'd like to know how long it takes them to separate. And to do this, we're going to use a little old-fashioned formula called distance equals rate times time. Time is distance divided by rate. The distance is 3,000 kilometers. The rate is 1 centimeter per year. I've got to deal with the fact that kilometers and centimeters aren't the same unit. What's the conversion factor from centimeters to kilometers?
Is it 1,000 kilometers per centimeter? Or 100?
It's 1,000 meters per kilometer.
Oh, okay, that's what I was thinking of.
It's 100 centimeters per meter. So how many zeros is that total?
5.
All right. Put them together and what do you got?
$3 million?
No, almost,
Billion?
but not quite.
3.
Once again,
Billion?
Adrian, I think you're typing in 10 exp5. That's not 10 to the 5.
Oh, it's Olivia, but
Oh,
it's okay.
Olivia, sorry.
It's okay.
It's not 10 exp5 there. That's
That's
one.
what I keep doing wrong. Yeah. 3. It's times 10 exp. No. Times 1.
Yes.
1 times 10.
That's 1 times 10 to the 5th. I agree.
Okay. That's what, yeah.
Or, Olivia, you could also just count up the number of zeros.
Oh,
5,
5, 8, 6,
Yeah.
7, 8.
which is the
That's
same
easier.
thing as 300 times 10 to the 6. What are my units here?
Kilometers and centimeters cancel out, so it'd be years.
Good. What's the follow-up question?
What are the global consequences of motion like this?
What do you guys think are the global consequences of the fact that the continents were once together 300 million years ago?
Would there be like, well, earthquakes from the plates colliding?
Yes, there certainly would. What are some other consequences?
Mountains rising, evolution taking different turns in different areas, tsunamis from the earth consistently changing from the earthquakes and volcanoes.
Yes. Yes, absolutely. In fact, Nick, if I looked at Earth 300 million years from now, I wouldn't recognize any of this shit, would I? Look
No,
totally different. And if there were mountains, they would change. If there were impact craters, they would get subducted into the ocean, worn away. I guess you might think of 300 million years as the time scale over which nature redraws the surface of Earth. This is what we call a geological time scale. Let's write that down. This defines a so-called geological time scale over which Earth refreshes its surface. For this reason, students, it is very unlikely to find any patch of rock on Earth that is older than 1 to 300 million years old. As a matter of fact, some of the oldest continental crust on Earth is currently right underneath your feet here in the state of Rhode Island. All of the eastern seaboard, especially the northeastern seaboard, is some of the oldest continental crust on Earth, because if you look at the boundaries of those tectonic plates, we're right in the middle of them, and it's been a long ass time since any of this portion of Earth's crust has been refreshed or destroyed. Much younger areas of the continent are like the West Coast, which is very close to a subduction zone. Okay. What do you say we take a little 10 or so, maybe even 15-minute break before we start lecturing? Just give ourselves a little pause. We like that, right? Megan's already on it. Okay, me too. I'll see you guys at like 12:15 or a little after that, maybe. Okay, I'm back. Today is our 10th and penultimate lecture. Our class on Wednesday will be the last one. Let's try to make sure we have all our homeworks and labs in a timely way, because by Friday, I'm going to want to wrap this up with a little bow and throw it over my shoulder, okay? As I'm sure you guys want to as well. We ended last class discussing, the beginning of the day, we're discussing the 4 geological processes. And we were also learning that the internal heat of a planet is related to the thinness of its lithosphere and the number of geological forces that you'll find on its surface. Today, I would like to talk about the 4 geological processes and then make a little transition into planetary atmospheres, if I can do it nicely and neatly. Let's see how we can do this. So we're going to start off here. Let's grab a slide. I like to start the day with a picture, a meditation picture. And we're going to think about impact cratering. One of the first things that we learn when we study impact cratering is that everybody gets hit, and size doesn't matter as much as you'd think it would. For instance, here's a picture showing you the far side of the moon, I believe, just riddled with impact craters all across its surface. Am I to believe that all of these impacts just happened to miss the moon? Sorry, let me try that again. Consider the moon and Earth side by side. The moon is covered with impact craters, whereas the Earth is relatively impact-free. Its surface does not show the kind of cratering that you see here. Am I supposed to imagine that all of those impacts missed the Earth, but happened to strike the moon? That seems kind of unlikely, that the moon would get struck with so many more impact craters than the Earth. The only logical conclusion to reach is that the Earth has been hit just as many times with these types of impacts as the moon has. The reason why the Earth does not show these impacts is because the Earth has other types of geology which can more quickly erase evidence of impact cratering. But Earth is being hit. When these impacts come from space, they usually take the form of some large chunk of rock or metal traveling through space at extremely high velocities. They strike the ground, and their kinetic energy is so high that they are kind of like the equivalent of a bomb. And the energy is capable of vaporizing rock into gaseous particles and maybe even liquefying some of the rock, melting it a bit, and excavating a large crater or basin and kicking up a blanket of ejecta and dust that will surround the crater in the form of those so-called rays. There's a bunch of little different notes I'd like you guys to take on impact crater. So the first of our 4 geological processes, impact cratering, we can start off by thinking about these key bullet points. The first is that all planets get hit. Size doesn't matter. And that's because compared to the vacuum of space, the planets are actually all relatively small targets. The difference between 2,000 and 6,000 kilometers is not very meaningful in comparison to a dartboard the size of an astronomical unit. However, not all planets show evidence of cratering today. And if you were to ask why, the answer is other types of geology erased it. That's not to say that impact cratering does not exist anywhere on Earth. In fact, when I was a college student, I went to my undergraduate studies at the University of Arizona in Tucson. And I was fortunate enough during one spring break to take a trip out to see this bad boy. I went with my father into the Badlands of Arizona, and we visited Meteor Crater. I don't know if any of you have ever been out west, but getting to see Meteor Crater is a pretty cool experience. Meteor Crater is a roughly 1 mile or a couple of kilometers sized impact crater out in the Badlands of Arizona. It's actually on private property. Some dude ranchers own this land that the crater is on, and they charge you $20 for admission to their crater. You basically drive up a highway, you have to pay them $20. They walk you through an alien keychain, I love UFO gift shop. And when you get to the edge of the gift shop, you can stand out on this observation platform and you can look over the impact crater. And it's pretty wild, I gotta say. It's kind of crazy to imagine. Here's a person standing on the edge of it for scale. It's incredible to imagine what it must have been like when that thing landed. It must have kicked up quite of a plume of dust. I think people have dated the age of this thing to maybe 60 million years ago or something like that. Comparable to when the dinosaurs were around, but not, this is not the impact that supposedly eradicated dinosaurs. That one would have been much larger. If you were to ask me the question, how often does Earth get hit? I would have to say that that question does not make any sense as stated. Because how often Earth gets hit depends greatly on how big of an impact you're talking about. This slide here ought to explain that a little bit. This slide shows the frequency with which objects strike the Earth. Every hour of every day, an object of size meter or more is striking the planet, but usually those are small enough where the atmosphere can vaporize or burn the rock and metal into dust. I would like to mention that a meter-sized rock is no joke, right? You would certainly struggle to pick up a rock 1 meter in diameter. In fact, it might be impossible for you to do such a thing. So a boulder strikes Earth every hour of every day. By the time they get up to 10 meters, which happens once a year to once 100 years, that's when you create a meteor crater size impact, a sort of small crater or an atmospheric explosion. If you look out every 1,000,000 years to every 100 million years, that's when you get hit with some big boys, something like a kilometer across. Now that's a dinosaur killing object right there, capable of creating tsunamis, climate change. And then maybe once in 1 billion years, once in Earth's history, you get hit with a big boy. And the big boys are capable of causing mass extinction, eradicating many species on a large scale. If we look at the history of life on Earth, and we study it by looking at the dispersed number of organisms found, say by looking at their fossil records, for instance, tell us about the diversity of organisms on Earth, we discover that there have been a number of so-called mass extinction events that have taken place over the last few 100 million years. There's a kind of cool Wikipedia read on mass extinction that I'll share with you really quickly, or extinction event. And it's got a pretty fascinating slide here. This is the extinction rates of marine organisms over the last, I think this is, vertical axis is percent of species lost, and time is in millions of years. So this goes back 500 million years. And let's look at the, oh shucks. Well, let's look at the results up here. So this is the extinction event that eradicated the dinosaurs. That's around 65 million years ago. That lost 30% of species. I think these are marine species lost. I think one of the craziest extinction events ever recorded in Earth's history was the Permian-Triassic extinction event, where half of maybe land animals were removed, and I think something like 80% of all marine animals were killed off. Just a huge number of species that were lost. Like, species go extinct every year on Earth. If there's one thing organisms do well, it's perish, okay? But there are weird periods in time where you have an inordinate number of species dying in a very, very short period of time. These little spikes are called extinction events. Now, what the hell could be randomly causing huge numbers of organisms to die out every, I don't know, 100 million years ago, or every 100 million years or so? Maybe stuff like this. That seems to somewhat correlate to the frequency with which these large impactors strike Earth. So something to think about is that nature periodically just wipes the board and starts from scratch again. One thing that it tells us is that the number of impact craters we see in some ways can indicate the age of a surface planet. So this is a key idea, and this is a key idea in planetary science. So I want to get it down before I forget and drift away from the topic. The density of impacts at a surface is an indicator of what I would call surface age. It's not the age of the planet, because they all have the same birthday 4.6 billion years ago. But some planets have a young planetary surface age, and some have an old age. So a young planetary surface will show a very low crater density, whereas an old planetary surface will show a high crater density. This is a key concept in planetary science. And believe it or not, planetary scientists, when they look at a surface of the world, will actually count the number of impacts per square kilometer as a method of indicating the surface age of the planet. Some other things to think about. Terminologies that go along with cratering. So here are some cratering terms. Three words that get bandied around a lot when you talk about impact cratering are meteoroid, meteor, and meteorite. Do you guys want to guess the difference, or anyone want to guess the difference between these three things? I'm assuming you don't know the difference between a meteor, a meteoroid, and a meteorite, but maybe there's a, oh yeah?
So wouldn't a meteor just be a regular, like, what you think of when you think meteor, big piece of rock falling into Earth? A meteorite would be a smaller one, and a meteoroid would be something that is like a meteor, but isn't quite exactly, I think.
It's a reasonable guess, Adrian, but it's a little off. If I were to sum it up, I think I could do it in one word for each of these. It's about what stage of the process they're in. Meteoroids are when the rock is found in space. A meteor is when they are flying through the sky and they create a fireball. The largest fireballs have a special term. They're called a bolide. A bolide is the term for a massive fireball. So, hey, ever heard of a shooting star? That's a meteor. That's when you see a fireball traveling through the sky as the rock generates friction with the atmosphere. There's a lot of meteor showers that happen at key times throughout the year. In fact, the big ones, the Leonids and the Perseids, are in August and December. So this, I guess we're in August now, right? Yeah, we saw a couple of meteors last week when we were observing. I set up the telescope and we observed Jupiter and Saturn at the rooftop down here. If you guys go to the wiki page for meteor showers, or I guess you could go to the American Meteor Shower Calendar, the American Meteor Society, people are, of course, excited about these things. And, you know, normally my lecture on meteors would have been part of a different lecture, but I won't get to that during this summer month. So I'm going to just throw it in here now. Come on, you stupid internet. There are some major meteor showers and some minor ones that happen each year. Oh. Sorry, guys. Let's try Wiki. That seems to work more reliably. So there are actually meteor showers that happen at the same time each year, and there's tons and tons of them. The big ones, in August, the Perseids, which are, I guess, technically going on right now, with a peak August 13th. So how far away is that? Oops, why are you doing this to me? That means next Thursday, next week will be the peak of the Perseids. And that means, folks, that if you spend some time out right around now, looking up at the sky, the chances of you seeing meteors at night are high. One thing I will point out about seeing meteor showers, the reason why they happen at key times each year is because meteor showers are connected to the orbits of comets, okay? So over time, comets, like Neowise, will break up and disintegrate into bits of rocks and pebbles. And those orbits intersect Earth's orbit at particular places during the year. As Earth travels through these ancient orbital paths of comets, they're littered with bits of rocky debris that came shooting off of the comet. And as Earth crashes into those bits of debris, those rocks strike the atmosphere and create meteor showers. Now, that's not the only place we can get meteor showers from, but I believe the Leonids come from the intersection between Earth and the orbit of Comet Tempel-Tuttle, which is now disintegrated. So in any case, because Earth, here's a funny statement, Earth travels in the direction of 6 a.m. So if this is 12 noon when the sunlight's directly on Earth, the terminator of Earth, where it's 6 a.m., is the same direction in Earth's orbital path around the sun. So the best time to see meteors is really, really late in the night, sometime between midnight here and 6 a.m. there. But you don't want it to be too bright out. So around 3 a.m. or 4 a.m. are the best times to see meteor showers. So it favors people like me who are night owls, who are willing to stay up late. A meteorite is once the object hits the ground. And once it becomes a rock, then it's a meteorite, Adrian. In fact, it just so happens that I have a piece in my hand of the meteorite that formed Meteor Crater. So this is a fragment of the meteorite that they found that came from Meteor Crater. This is what's called an iron meteorite. It's almost entirely made of iron. You'll see here that while it's not the meteorite, to answer your question from last week, Tim, is not magnetic, but magnets will stick to it because it's made of iron, and iron is ferromagnetic. And this shows you that meteorites are not always rocky. They can be rocky, or they can be metallic, or some combination of the two. The study of meteorites is like a whole thing, and people get kind of excited about it. Some are rich in carbon. Meteorites, I'll just tell you the short story. They seem to have one of three origins. There are some meteorites that are bits of rock that have just been kicking around since the beginning of time. Those are primitive meteorites. Then there are meteorites that seem to be broken off pieces of asteroids. And then there are meteorites that seem to be burst off the surfaces of planets. You wouldn't believe it, but 20% of all meteorites found on Earth have a chemical composition identical to the surface of Mars. These are the so-called Shergatti meteorites that are basically just pieces of Mars that got blasted off of its surface and eventually drifted their way down onto Earth while orbiting the sun.
Did we ever get hit with anything from the Kuiper Belt?
Yes, absolutely, because the Kuiper Belt produces the so-called short period comets, like Halley's Comet, and those are a rich source since they're in the same plane of the ecliptic. Those comets most frequently are interacting with the orbit of Earth. So pretty much all of those major meteor showers of pieces of Kuiper Belt comets. Sometimes pieces of asteroids make it to us as well. Sometimes little just crazy. They could actually, some meteorites probably have a very low percentage, could even have an extrasolar origin and come from a neighboring solar system. We now know that the Oort cloud is a larger reservoir of comets that's greatly outside the solar system. And some of those comets can go half the way to Alpha Centauri. So we're starting to realize more and more that there are interstellar travelers, at least in the form of rocks, that make it to our solar system. They are a much lower percentage of the time, but they are out there. I want to show you guys a cool video, a couple of cool videos, just to kind of keep things switching up here. There are many cool YouTubes of meteor impacts, but one that I think is nice and representative is a meteor impact on a police camera in Canada. Let's see if that's enough to, yeah, this is, so this was a few years back over Edmonton, Canada, and I want you guys to just watch this little video. They're going to show it and loop it twice, and I think it's worth checking out. It's just a camera on a police car that captured this, and I want you to watch this sucker as it strikes the atmosphere. The fireball from that meteor is so bright. Here it is in slow motion. It's bright enough to set the entire nighttime into day from the intensity or luminosity. And that's one of the ones that probably left behind a small piece of meteorite behind it. By the way, meteorites are very valuable to scientists and meteor collectors. So a 1 kilogram chunk of a meteorite can fetch tens of thousands of dollars in rock collecting communities. So hunting for meteorites can be profitable as well as fun and scientific. When we think about these things, one other thing I want to do while we're doing some terms, okay? When you actually create an impact crater, there's a couple of key parts of your impact crater that are worth talking about. And these terms will come up in our class today. there's the rim of the crater. You excavate a basin. Sometimes as we saw on the moon, the meteorites will leave behind a central peak. And they can also throw out a blanket of, sometimes we call it ejecta, and sometimes we call them rays if they fan out like spokes from a wheel. So those are some key terms that you'll hear me use when discussing craters: basin, rim, rays, ejecta, peak. There's an interesting question about the moon's surface, and you guys now have studied the moon with me. So let's see if we can call up that picture from our last class. Where's the labs here? That nice HR Astro image of the waxing crescent moon. Let's zoom in here and let's just take a look at some of these maria. So there are two types of lunar terrain. There's the lunar maria and the lunar highlands. What do you suppose is the younger surface? The lunar highlands or the lunar maria? Is this patch of the moon younger? Or is this patch of the moon younger? No?
The one on the left is younger.
Oh, you don't know which is which?
The one on the left is younger.
Yes. Yes, this is maria, right? And these are highlands. But let's think about this in terms of that homework problem we just did. We learned that there's no erosion on the moon, nor is there much volcanic activity or moonquakes. By the way, the lunar expeditions did put seismographs on the moon, which subsequently detected no moonquakes of any type. There's no geological activity happening on the moon. Not today, anyway. But that gets me thinking, Tim. If this is an old surface and this is a young surface, but the moon's been sitting around for a long time, like, I don't get it. How did the moon, what type of activity created the smoother surfaces of the maria? Why are there no, am I supposed to imagine?
A larger impact a longer time ago?
But if it's longer, it would be exposed to more impact cratering since then. You don't mean to assume, Tim, that all of the impacts just happened to then strike over here, right? But they all missed here? Doesn't that seem weird?
No, there was a larger impact on the maria that sent everything else to impact like the highlands and the area surrounding it.
That's true. So that's not wrong, Tim, but here's the conundrum. If those impacts happened a long time ago, why haven't these things filled up with craters since then? The moon didn't get hit yesterday, and yet it looks like it got hit yesterday. Because, well, if it got hit yesterday, you'd expect some of this stuff to still be molten rock or something, I guess, right? Do you see the problem, Tim? If it got hit, as you said a long time ago, based on the rate at which craters are striking the moon, we would expect to see craters here. And we do see some craters in the maria, but not as many as you'd think. To address this question, the lunar astronauts actually set out to get samples from the maria and samples from the highlands. And this is what they discovered. They discovered that for the age of the moon's surface, that the lunar highlands, sure enough, were older. They clocked in at 4.6 billion years old, and we did that through radioactive dating. But the lunar maria they must have formed around 3.9 billion years old. Tim, the question becomes, why in the subsequent 4 billion years did the Maria not also fill up with cratering?
Is that, I don't know, is that the window? Is 750,000 years?
This isn't thousands, this is billions of years, right? We're talking billions.
Oh, yeah.
Billions. Here was the solution to the problem. Enter in a hypothesis known as the heavy bombardment hypothesis. This is important because it plays a big role in understanding planetary science. Heavy bombardment was a period in our solar system's history from 4.6 to maybe 3.9 billion years ago, at which point people believed that the rate at which impacts struck the surfaces of planets was much, much higher than it was today. In other words, today we might get hit by one of these big sized meteors, a kilometer sized thing every billion years. But if you went back in the history of the solar system, it must have been a much more messed up place with many more meteoroid chunks sort of left over from the formation of our solar system. And you might think of these things as overgrown asteroids, things that didn't quite make it into planets. They would have hurled down and smashed all across the surfaces of the planets. And today, whenever you see that really, really heavily cratered terrain like you see on the lunar highlands, that's indicative of the heavy cratering of the heavy bombardment period. Let's do that as a note. The heavy bombardment period is a period in the solar system's history from roughly 4.6 to maybe 3.9 billion years ago, when a much higher frequency of large, we'll call them meteoroids, collided with the surfaces of the planets. Heavy bombardment period is directly responsible for the formation of major highlands on much of the planet's surfaces. We see evidence of heavy bombardment on the moon, on Mercury, and to some extent, we see some of these highlands on Mars as well. Mars did not completely eradicate its heavy bombardment. In other words, we believe that the intense cratering that you see in certain parts of Mars over here, that's all from heavy bombardment in the early solar system. It must have taken Earth its entire 4.5 billion year lifespan to erase all of this stuff and create the smooth, clean planet that we have today. In any case, impact cratering tends to be the default geology of planetary surfaces. When you look around the solar system and you see weird objects like, I don't know, let's just pick a random object. Let's pick
Enceladus.
Thank you. Enceladus is a moon of Saturn. And based on our simplified knowledge of, I should show you a color image because they're way cooler. Come on, they've got to have a color image of Enceladus. Oh, yeah. What do you think, Tim? Does Enceladus show a young or an old surface age compared to other bodies in our solar system?
It looks like it's got a little bit of both, but I would say younger.
Yeah, this stuff is all clearly really, really young. And you can see that some of the ice has melted and formed some small streams or rivers here, right? But this stuff, Tim, that's almost heavy bombardment there, right? So
Yeah.
This part of Enceladus is wicked old. This part of Enceladus, don't you think that's young? I mean, sorry, don't you think that's weird that all the young surface would be like smushed to one side? You see this a lot of times in moons of Saturn, that moons of Saturn show a kind of two-toned surface with extreme differences in geology from one side to the other. Another one is Iapetus. Iapetus is one of my favorite moons in the solar system. And Iapetus just looks absolutely crazy. It's got a young surface, but it has a two-tone surface with extreme type of geology affecting one side. And by the way, this side here, the dirty side, that's the side that it's moving in the direction of. So there's reasons for this stuff. You can see there's some craters up here at the top. Here's a massive crater that looks like it's been chipped away by some kind of erosion. In any case, your first step of learning planetary science is to learn that when I see craters, counting them is the first step to saying, what happened here? Am I looking at a young or an old planetary surface? After that, you can start looking for some of your other types of geology. Let's list some of that before I run out of time. Okay, so let's say some good words. And obviously, guys, if you took a geology class, you would spend many, many weeks discussing each concept, volcanism, plate tectonics. This is going to be a really bubblegum candy version of a proper geology course, all right? So let's talk about volcanism. Volcanism kind of takes three forms across the planets. The forms it takes are volcanic plains, shield volcanoes, and what are called stratovolcanoes, which we find on Earth. Volcanic plains are types of volcanoes that have no dome. It's basically just a lava pool. Shield volcanoes are the tallest types that have gentle slopes, but extremely flat plateaus. So they are tall, but I guess they're gently sloped. I don't know if shallow is probably not the right word. Tall but gentle sloped. For some reason, I can't think of a better way to say that. Stratovolcanoes are often the types that you see on Earth. They are shorter, but pointy. So I'm just trying to distinguish these types of volcanoes so you realize they kind of come in three flavors, okay? Some things that all volcanoes have in common. Well, let's just imagine your hypothetical volcano. They form when you have cracks or what are sometimes called vents in a thin lithosphere. And typically they take a form where they form some kind of a dome The opening of the volcano is called the caldera. And then you frequently have, you know, like a vent which goes down into the mantle, a magma chamber. I don't think this is called the vent. I think this is called like the pipe or something. I think that's right. They sometimes have side vents which blow off the side. Basically what's happening is underneath the Earth, you have zones of convection which are bringing warm rock up to the bottom of the lithosphere, and the lowest density materials, things like carbon dioxide and water, start to melt the surrounding rock and create a pool of lava inside the magma chamber. That then builds up pressure and steam until an eruption happens and the top blows off the volcano. It's important to recognize that volcanoes are responsible for two things. Hold on a second here. I had to hide the non-video participants because they were growing. Volcanoes, from a planetary science perspective, have two key effects. They erupt and release lava, and lava is capable of repaving planetary surfaces. We'll see in our lab today that many areas of Mars are smoother than their surrounding areas, and the smooth areas tend to be surrounding the volcanoes, as if to suggest that the eruptions of lava just covered up all of the former cratering and mountaining that you see in the surrounding area.
Isn't there a Jovian moon that does it, like it has so much volcanic activity that there's no craters?
Yeah, that's the moon Io, which is extraordinarily, in fact, Io, which I'll get to at the end of our lecture, Io is more volcanically active than even Earth, which is itself kind of a cool story. The moon Io, every black dot that you see here is an active volcano that spews off sulfur dioxide, which then freezes out and rains back down on the surface. Io is an interesting example of a very volcanically active world that doesn't have much of an atmosphere. That's kind of a conundrum. Usually volcanoes and atmospheres go hand in hand, and that's got something to do with the magnetic field of Jupiter, and we can talk about that a little bit later. And Io plays into that discussion, Tim, in that the other effect of volcanoes is outgassing. And outgassing releases gas that usually is responsible for forming a planetary atmosphere, provided your planet can hold on to it. So the types of gases produced draw a little picture here of a volcano spewing out gases. The key principal gases produced are H2O, water, CO2, carbon dioxide, sulfur dioxide, what else? Nitrogen, argon. There's probably some others I'm not thinking of. But water, carbon dioxide, sulfur dioxide are some very popular gases. pure oxygen is not a volcanic gas. That's something to think about. Now, one of the reasons that we form different types of volcanoes has to do with the density, I'm sorry, not the density, but the viscosity of lava. And the viscosity of lava is related to what chemical compositions it's made out of. For instance, excuse me here. This is a type of rock. This is what lava forms once it cools and solidifies. It's called basaltic rock. You see it's porous. It can be made of different elements. Do you guys remember what the primary mineral is that makes up most rocks on Earth? It's related to the term silicates. It's silicon dioxide. Here's an example of two different types. I thought you guys might remember what a silicate is, but I guess not. Too ambitious. Here's a form of lava. This is a very thick and high viscosity. Viscosity is the resistance to flow, right? Honey has a high viscosity and soy sauce has a low viscosity. So here's a high viscosity lava. Lower viscosity lavas can travel for many, many kilometers before they cool and solidify. And that's what determines if you can build up a dome, and if so, how big of a dome you can build up. Hawaii is an example, the main island of Hawaii is an example of a shield volcano on Earth, whereas Mount St. Helens is an example of a stratovolcano, a short but pointy one. And you'll notice that they're both comprised mostly of silicon dioxide, but they have different quantities of metals in their metallic content. I believe the aluminum oxides can actually have a big effect on the viscosity of lava. You'd have to ask your geology professor more than me, but these metal ratios will change the viscosity of lava and determine whether you can build a short pointy volcano before the lava cools off, or whether you can form a big shield volcano, or even just not even make a dome at all. So it tends to be that volcanic plains are formed from low, or let's not call it basalt until it's frozen. Let's call it low viscosity lava, medium viscosity lava. And stratovolcanoes are produced by high viscosity lava. If you guys look at where volcanoes are formed on Earth, you'll find that there's two different mechanisms for forming volcanoes and two different places where they can be found. Let's see if I have a picture of this here. One place you can find volcanoes are what are called convective hotspots. And that tends to be locations on Earth where convection is driving warm rock up in the same sort of locality. This tends to put pressure on the lithosphere and create fractures and vents that can form volcanoes. Now, plate tectonics will push these things over the convection, and that can tend to form a chain of volcanoes, which might take the form of an archipelago in the ocean. An example of which could be the Hawaiian Islands, right? If you guys think about the islands of Hawaii, you can actually date the ages of Hawaiian Islands as they travel over the surface of Earth. So the main island of Hawaii is maybe 200,000 to 700,000 years old, whereas some of the further off volcanoes, which are lower in elevation, can be 1, 2, 3 million, 4 million years old. So you can actually see that the volcanoes are shrinking and getting older as you get off the main island of Hawaii. What that suggests, of course, is that there's a convective hotspot somewhere over here, And as the crust of Earth is being pushed over this hotspot, volcanoes are forming in the Pacific Ocean, and then they're slowly being worn down over time. In fact, there's a new volcano which is formed undersea just next to the main island of Hawaii, and I believe it's called Lohi. And Lohi is scheduled to poke itself up out of the surface of the ocean sometime in the next 1,000,000 years. And that'll be basically a new Hawaiian island for us to go surfing at, okay? The other places we tend to find volcanism on Earth are near what are called subduction zones. And I think a picture would be helpful here. Not only do we find volcanoes in random spots where there's upwellings of convection, but any place where the oceanic crust gets pushed underneath the continental crust, it tends to trigger volcanoes and form a bunch of volcanoes especially along the west coast of the North and South American continent. In fact, there's a location on Earth called the Ring of Fire, where we see the greatest amount of volcanic and tectonic activity on Earth. And the Ring of Fire, the Pacific Ring of Fire, is found all along regions where subduction zones are pushing Earth's material down underneath the crust of Earth and triggering epochs of volcanism all along these trenches here. This means that on Earth, there is a symbiotic relationship between plate tectonics and volcanism. They feed one another. This is also the region where we find the greatest number of earthquakes. As I showed you during our office hours, the Ring of Fire can actually be seen traced out here at the boundaries of our lithospheric plates. Okay, I would have taken notes on that, but I'm pressed for time, so let's leave it here for volcanism, and let's move on to plate tectonics now. I'm just kind of giving you a little bits of information about all of these things, and we'll start atmospheres after lunch. Okay, what can I tell you guys about plate tectonics? As I mentioned in last class, a full, robust set of plate tectonics is unique to Earth, but we do find what I might call tectonic features. Not a complete set of plate tectonics, but we find tectonic features or cracks on all planets and moons. If you look hard enough, you can find tectonic-like features on almost any planet or moon. So a robust set of plate tectonics is unique to Earth, but that doesn't mean you won't find these fissures or cracks anywhere. Usually you can tell the telltale signs of tectonics. They don't quite look like rivers, but they tend to look like this. Places where you can see sharp, jagged cracks or gashes, wrinkles due to mountains or giant scars or rips in the surface of the planet. Usually those are tectonic, and you can tell the difference between tectonics and erosion is erosional features kind of resemble rivers on Earth. They're serpentine and S-like, they're curvy. Tectonic features tend to be a bit more jagged and cracky, a little more hard-looking. Now, here's how plate tectonics works on Earth. Earth's lithosphere is fractured into a set of approximately 10, we call them lithospheric plates. That float on the convective asthenosphere, which is kind of like the mantle, the upper mantle. Now, these plates are driven forward by convective bubbles on what is sometimes known as the conveyor belt model. So the plates are driven around Earth by convection on a conveyor belt model. I was going to try to draw that, but in the interest of time, I'll just show you a quick screen share. Oh, bloody hell here. Here we go. Here you can see the seafloor crust floating on the asthenosphere, which is driving it along and pushing it forward. As these seafloor beds smashes up into the continental land masses, it's scraping up lighter density silicates in the form of sand onto beaches and pushing down into subduction zones, the heavier, denser parts of the seafloor. Keep in mind that plate tectonics does not mean that continents are floating on the ocean. Notice, for instance, that the North American plate consists of the continent of North America, but it's stuck to the seafloor bed all the way out to the mid-Atlantic ridge. So the tectonic plates include continents plus seafloor bed. However, there's no denying the fact that continents are formed in part, maybe entirely, by plate tectonics. So effects of plate tectonics are they smash together, they cause, obviously, earthquakes are a result of plate tectonics. They form mountains, continents, and so-called rift valleys, where there are great depressions in the earth caused by lithospheric plates pulling apart. The Red Sea in the Middle East is an example of a rift valley where two continental plates drifting apart are creating a big depression which is full of water. So many cool surface features on Earth can be attributed to these plate tectonics. I guess what I'd say one of the net effects for planetary science is they tend to repave Earth's surface over something like a 100 million year time scale. And that's the geological time scale that we discussed in our office hours. I probably could say a lot more about plate tectonics, but I don't think I will. By the way, I don't know if you guys have heard of these subduction zones form some of the deepest locations in Earth's oceans. Have you guys heard about the fact that James Cameron, the director of Avatar, built this crazy torpedo submersible that they dropped into the Challenger Deep in the Marianas Trench? Going down inside one of those things is like going down inside of a subduction zone. I think the way this works, let's see if I can do a share screen. So so here's the top. Oh, let's erase that here. Let's choose a color appropriate for the ocean. The tops of the oceans are maybe at the deepest places 4 kilometers to the bottom. We're talking about the middle of the Atlantic Ocean after you drop off the Atlantic shelf. So some of the, I don't want to say the absolute deepest, but the bottom of the ocean is typically something like 4 kilometers from the top of the waves, right? But then you'll just have these trenches that might drop off another 7 kilometers. And it might be 11 kilometers below the surface of the ocean. The pressures are so great down inside these trenches that not many organisms can survive there, and not many submersibles can reach this depth. Up until recently, there are only a few man-made objects that have ever gone to a depth like this. And the director of the Titanic, James Cameron, built himself a torpedo and personally piloted the thing, Evel Knievel style, down to the bottom. There's a whole National Geographic on it, and it's totally wild. I think it's called the Deep Sea Challenger. What was the name of his craft again? Did anyone watch that? Pardon?
Challenger Deep.
The Challenger Deep, that's right. And you guys can read about it. And he took a whole bunch of footage from the project and turned it into some kind of National Geographic. The Challenger Deep is the place he went to. It had been visited once before by a what do you call it? Bathysphere, bathyscape, some kind of a very low depth submersible. I wanted to. They've sent some autonomous vehicles down there, but the number of manned missions. Whoa. I was not expecting this to be as intense.
Oh, it's Deep Sea Challenge.
Deep Sea Challenge, thank you. Deep Sea Challenger, okay. Yeah, and this is a whole program that you can watch on National Geographic about his torpedo and his expedition down to the bottom of the ocean. It's super cool. I recommend it. They discovered all kinds of new science, found all these new organisms down there. And he's a director, right? This is not a scientist. Well, he is kind of a scientist now. He's a movie director who just decided, I'm going to take all my money and use it to go to the lowest point that anyone's ever been to in the ocean and get these giant tube worms and stuff. I'll have more to say about those things later. So that's almost like too crazy to even be true. You know what I mean? It's like such a cool story. But he basically went down inside one of those subduction zones. And by the way, some of the bottom of the seafloor actually has underwater volcanism, places where the lithosphere of Earth essentially shrinks to zero and the convective mantle is bubbling up. You even have boiling water at some of these locations. One of the most famous locations, of course, they're called hydrothermal vents. And the Mid-Atlantic Ridge is one of your classic examples of a hydrothermal vent. These are regions where subduction zones are basically like little underwater volcanoes, which are forming new pieces of the seafloor crust. So here's a picture of there are white smokers and black smokers. This is probably sulfur dioxide bubbling through volcanic vents at the bottom of the seafloor. And they have a nice model here of a hydrothermal vent community. This is actually going to come up in our lecture a couple of times. So here what you can see is you'll have like a magma chamber. Look at the temperatures, 1200 degrees Celsius, pushing a mixture of seawater and gas and lava up to the surface where we find these black smokers, and you'll have a column of gas just bubbling up. The temperature of the water at a black smoker could be 350 degrees Celsius. And that's at the chilly bottom of the ocean floor. You suddenly have a boiling water underneath the ocean. And what's really cool is we discovered a aquatic series of life forms living in these hydrothermal vent communities and surviving off the geological activity of Earth. Weird translucent crabs that can survive crazy amounts of pressure, beautiful tube worms. It took us a while to figure out how these organisms were living without the aid of any sunlight. But basically, there are these microorganisms that eat sulfur dioxide in the volcanic outgassing. Then the tube worms eat the little microorganisms, and the little crabbies and shrimpies come along and pick at the tube worms. This is an entire ecosystem that is divorced from the solar food chain. They are literally feeding off of the geothermal energy of Earth.
Because that exists, doesn't it make it more possible for like under Enceladus that we could find something like that?
Yeah, we think the most likely places to find life today are not even Mars, but underneath the ice surface of Europa, possibly Enceladus, and possibly Ganymede. We have some evidence that they might have under ice oceans that have been sitting down there for billions of years. And exactly, Tim, we believe that most likely life existed on Earth in the early stages along these geothermal vent communities because there wasn't enough oxygen in our atmosphere for photosynthesis. So if it could happen here on Earth, and if there are similar hydrothermal vents on Europa or under the ice in Enceladus, then yeah, there could be a whole ocean of aliens that we have not discovered yet. And by the way, in preparation for our final lecture, if you guys want to have a really exciting movie experience, I would recommend highly an indie movie called Europa Report, which imagines the first hypothetical manned mission to the surface of Europa to drill underneath. This is going to happen someday. We are going to drill underneath the ice here to attempt to find if there's any possible organisms living there. So they send this crew. It's all told from point of view cameras, kind of like Blair Witch. I'd say the movie is like Blair Witch meets 2001, and it's real scary, man. Bust out the anchovy pizza and beer and put the kids to bed, because it's kind of spooky when they actually get to Europa and start drilling down under the ice. It's the science of Europa Report is 100% good planetary science. There is nothing preposterous or unrealistic about it at all. And the movie is cool and doesn't suck. So I would really have you seen it, Tim?
Yeah, I have. It was really good.
Really, really good. So if you're a sci-fi fan, it's a must-do. And even if you're not a sci-fi fan and you're just interested in the things we're talking about, it's actually pretty informative, if you ask me. Okay, before we take our lunch break, let me just say very, very quick words about erosion, and then we will have covered all of geology and we can move on. Erosion is a powerful and fast-acting form of geology on the surfaces of many planets, not just Earth. Erosion can take a number of simple forms. It takes the form of wind. Wind actually can destroy rock, okay? As anyone who's been caught in a sandstorm knows. Wind, water, and ice. But I'm going to cheat a little, and I'm going to include a fourth type that we see as we get further out to weirder bodies in our solar system. On a lot of moons of the gas giants, we see planets that have no atmosphere but do have wind erosion, which is a very, very weird conundrum. And we believe these are being caused by frost jets. And the idea is on frost jets that you'll have a bit of ice. On a warm day, the ice will sublimate into gas. The gas will blow across the surface, creating erosion, and then it will deposit back into the form of ice. So it's basically like a temporary wind on planets that don't have an atmosphere. Erosion is active today on if you exclude Jovian moons, because we're still supposed to talk about terrestrials right now, Earth and Mars are both active in terms of erosion. Earth, of course, has all three, where Mars's erosion today is primarily in the form of wind, since it lacks water and ice. Venus is a weird case of a planet that has a very thick atmosphere, but no erosion whatsoever. And that's because Venus doesn't rotate, so there's essentially no wind. There's no water because it's too hot. And there's no ice. So without wind, water, and ice, Venus has remarkably low levels of erosion for a planet with a thick atmosphere. Erosion can reshape the surfaces of planets. When it comes to wind erosion, one classic example is something that I saw when I took my first trip to Arizona when I was 18, when I went to college out there. And I saw some things that I never saw growing up as a Rhode Islander. One thing that made a big impression on me was a dirt devil, okay? Now, I'm guessing if you're a born and bred Rhode Islander like me, you might not have ever seen a dust devil or a dirt devil before. But let me show you a picture of one here. In fact, the one that I saw was similar to this. I'd say it was kind of like this. I took the shuttle bus from Phoenix, Arizona, down to Tucson, Arizona. So it's like a 3-hour drive through the desert. I had never seen anything like it before. It's all this dirt and brown. And I was sitting next to an old cowboy who was on the ride with me there. And I looked out the window and I saw this thing that looked like a funnel of sand. It looked like a little tornado. And I said, "Is that a tornado?" And the old guy next to me said, "That there, son, is a dirt devil." And I said, "Well, what the hell's a dirt devil?" And he said, "I'll tell you what, son, I wouldn't want to get caught in one of those. It'll take the paint off your car or the skin off your face." Okay, so in other words, he was telling me there's so much sand getting kicked around in there that it will literally blast the paint right off of your car. And I know if you've spent some time in Iraq or Afghanistan, you might have seen some similar types of wind phenomenons. They have pretty epic sandstorms over there, right?
Sandstorms, yeah. I didn't see any dust devils though.
Oh, so I don't know if they're restricted to the Southwest of America or if they're found in other desert climates as well. But they are so freaky because it's like seeing a little tornado and they just kind of blow all around the desert and you're hoping they don't come your way. I want to show you some of the weird effects of this. So let me show you something cool. I want to show you 2 images of Mars taken a month apart in maybe 2001. Where am I here? I've got so many images in this slideshow. Okay, check out slide 107 here. This is a picture of Mars taken in June of 2001, followed by an image taken September 2001, both with the Hubble Space Telescope. In the first image, you can see all of the various surface features you're going to look at in lab today, including ice caps, volcanoes, and valleys. The second one, all you can see is a giant ass planetary dirt devil. It's a dust storm that's covering the entire surface of Mars at once. Now, because of this, the sandblasting on Mars, the wind pressure is much lower than on Earth's. A gust of wind could easily blow you over on Earth if you're in an intense storm. But on Mars, wind doesn't have that kind of pressure. But there's a lot of dirt and a lot of wind. And if you look at the rocks that you see on Mars, okay, I was hoping I had a picture here. Let me just type in here. I want you guys to notice a key difference this is from the Curiosity rover, the difference between what rocks look like on Mars versus what rocks look like on Earth. And here we go. Okay, let's get a zoom in. This is a very, very high resolution picture. Here's a picture of a bunch of rocks that you see on Mars. And you have to admit, guys, you would never see something like this on Earth. What makes these rocks look different than rocks that you'd see sitting around on the ground on Earth? Tim, do you see what I'm getting at here?
There's very little rounded edges.
They're wicked sharp and pointy, right? They're almost like arrowheads or flints. And that's interesting because on Earth they would be well-rounded. And what's that say to you then, Tim? Why
They're not getting worn down. There's no other type of erosion on the rocks.
Well, here we want to be very careful. There's no liquid water erosion, okay? Now you would see think about the pebbles that you find in a brook. They're extremely smooth from being worn down by water. So it's liquid water, Tim, that gives them that rounded edge. But before you say there's no erosion, Tim, let's look up close at the surfaces of some of these rocks, and you're going to see details that would surprise you. Let's just go back here to this picture, and let's see if this will do it justice. I want this picture, but I want a higher resolution version of it. Okay, this one will do me. Can you see, Tim, I don't know if it's translating over the internet, that this picture, maybe I should put it into the chat log. If you look at that picture up close, you can see that the rocks are covered in small, tiny pits. Can you see that? It almost looks like coral or something. Maybe you might have to click on the link that I just sent the class. Can you see all the pitted? Let's just see if we can just call up a high resolution image of a Mars rock.
Yeah, I can see it on the left.
They're covered in, this is, whoa, rare Martian meteorite, $34,000 on eBay. Well, those are inclusions. Those are something different, but yeah. The surfaces of Mars rocks, they look all chipped away by erosion. They're all sandblasted. Here's a good example. Yogi rock. This does not look like an Earth rock. Not only is it more jagged, but you can see the surface here has all these little inclusions and abrasions in it. And that's just due to dust devils, due to dust storms, blasting little grains of sand at this thing for years and years and years. So the pebbles aren't smooth, but Mars still does have erosion in the form of wind. That was a key idea. Of course, on Earth, water is capable of carving out canyons, and the glaciers, ice in the form of glaciers, are responsible for carving out many of the mountain features, like the Rocky Mountains that we see today. So primarily, ice takes the form of the movement of glaciers. They drag large boulders with them over slow time scales, and they deposit the boulders and scrape out the surfaces of the mountains. Ice can even split rock under some circumstances. Okay, at this point, we've done planetary geology. And when we come back from our lunch break, we'll start getting into atmospheres, because I really want to make it to the Jovian moons for our final class. That's what I'm trying to race towards, so we can spend more time talking about Enceladus and Io and stuff. It'll be, there's still more that we have to learn about atmospheres, but we'll do that starting after break. So I'm going to pause the recording. Hello, everyone. All right, we got Tim back in the house. Who else is here? Adrian, cool. All right. Now you're hiding from me again.
Do you remember when Eros changed its orbit and crashed into Venus, and the protomolecule built the ring gates?
Yes, yes, I love that.
Could you actually spin up an asteroid like Eros to have enough gravity to support? Like, I mean, it goes too close to the sun where it would be too hot anyway, so it doesn't make sense that they could live on that thing.
Does Eros, what's the perihelion of Eros? Well, I mean, you could live under some extreme conditions if you had environmental controls, but Eros is in the asteroid belt, right?
It's
I don't think that
1.1. It's 1.1, but I was looking at surface temperatures.
Oh, right. Well, that's actually going to be in our lecture coming up. So, remember, so does it say that the surface temperature of Eros is outrageously hot?
not outrageous, but 100 degrees Celsius.
That's that's fine. Well, I mean okay, so the reason for those extreme temperatures are because of probably the low albedo of the surface, right? So at just over 1 AU from the sun, 1 to 2 AU is totally within the habitable zone in our solar system. And the high temperatures are caused by the fact probably that there's no rock. There's no atmosphere.
Oh, yeah, that's true.
Right? So you're just sunlight beating down on rock. We're actually going to talk about this in this upcoming lecture segment.
How fast would
temperature can reach?
Did we ever cover that?
What?
Like rotational gravity? Like how fast you would have to be spinning?
Well, a little bit. We are going to deal with that's kind of part of the three things that I would want to talk about. So, Eros's rotation, like they should give you what the effective G's are on the planet. I mean, asteroids tend to be quite small, so their acceleration due to gravity is kind of low, right? I don't think you could jump off Eros, but
well, in the books they spun it up so that people could live on it or function. It was like a quarter G or something like that.
Right.
Is that a possible thing, or is that purely
that is possible? It's possible that you can use rotation. So I'm sorry, I didn't realize that you read the books. I just watched the TV show. Did you read the books?
Yeah, I read them. I mean, I've seen the show too, but I started on the books.
So it is very possible to use rotation to create artificial gravity. It took me a moment to understand what you were talking about there. If you could speed up the rotation, then you could create a base in a circular form, which would mimic gravity. You would just need to rotate so that your centrifugal acceleration was essentially 9.81 meters per second squared, right? But that's the premise of how they do it at the beginning of, and this has been a proposal for spaceships for years, at the legendary opening sequence of 2001, A Space Odyssey with Stanley Kubrick. I bet we could just find this 2001 opening sequence. Let's just see if this, just in case some of the youngsters here don't know what we're talking about. At the beginning of 2001, A Space Odyssey, they have this rotating spaceship. Here, let's just show the students. So here you can see a spaceship proposal where you have a cylinder, and it's rotating at such a rate as to cause the acceleration that, you know, like when you go to the amusement park and you're on that, what is it called? The gravitron, and it spins you to the wall. That's a very real feeling acceleration. And you could create yourself a base in which a person could, let's see if they have the show here. Oh, I was hoping they'd show that there's a sequence with the astronauts inside of the rotating spaceship, and they're jogging along the outside of it because they're experiencing an artificial gravity. If you climb in towards the center, the gravity would go to zero. So Tim, having not read the books, I wasn't aware that they created artificial gravity there. They didn't, if they explained that in the show, it was so quickly that I missed that detail.
Yeah,
But
most
yes,
of the places on show, like, I think even like Callisto, or no, they had enough gravity there. But the
Yeah, Callisto
smaller
would be enough gravity.
objects, Phoebe.
That series was pretty, the science of it seemed pretty realistic to me. There was nothing that was just totally outside the bounds of science as far as I could tell, which made it really cool and enjoyable. I freaking loved that show. I was so into it. But yes, it would be possible to live on Eros if you had a base. You'd have to sort of protect yourself from some solar radiation, but that's the same issue you'd face on the moon or even Mars. Both the moon and Mars don't have a magnetic field, and they have very low atmospheres to no atmospheres. So you'd be subject to particle radiation from the sun. In fact, that was in the Europa report too. When the scientists are exploring Io, They're subject to particle radiation not only from the sun, but also from Jupiter's powerful magnetic field. And that would be an actual threat to astronauts. When astronauts go on spacewalks, they are limited in the number of hours they can spend outside the spacecraft because they are exposing themselves to dangerous solar radiation. Hell, even pilots have a maximum number of hours they can fly per month due to the increased exposure to radiation you get as you travel up higher in our atmosphere. So that's definitely a real thing. But today we'll talk about what makes the surface temperature of a planet hot. And it's a combination of 3 factors that I mentioned in Wednesday's class: your distance from the sun, your reflectivity, your albedo, and also whether or not you have an atmosphere and have greenhouse gases. So let's start by just talking about terrestrial atmospheres together. So if I'm going to talk about terrestrial atmospheres, which of our terrestrial planets have atmospheres anyways? If we're just restricting ourselves to these guys, which of the terrestrials have atmospheres?
Earth, Mars, and Venus.
Earth, Mars, and Venus. So Mercury and the Moon essentially have no atmosphere, so we're gonna neglect them in the subsequent discussions. By the way, today's lab is going to be on Mars topography. So if you go to the Mars, where are we here? It should be called Landscapes of Mars. We're actually going to need this entire thing. We're going to need all these questions. You guys, since we're just going to be writing word answers in, some of you had some good experience before using a word editor to just put words in and then print that. So you can do that if you want. I might actually print out a physical copy just for kicks and giggles. And since my printer takes a long time, I'm just going to start doing that now. Okay. So let's grab the atmospheres lecture. One of the things that I want to say, well, maybe I'll say that next time. I'll talk about the fundamental planetary properties. Let's just take a look at the atmospheres of the different terrestrial planets. And what we want to do is we want to compare Venus, Earth, and Mars to see what their atmospheres are made out of and how they might be different. You'll notice here, we should take this as notes as well, that Venus and Mars have very similar atmospheres, almost entirely carbon dioxide, whereas Earth has an actually very small amount of carbon dioxide in its atmosphere. And these constitute something of a planetary mystery. Let's take some notes. So we're going to restrict our discussion to terrestrial atmospheres to start. Although many of the stuff we learned about applies to Jovians as well. Venus has a thick atmosphere. Earth has a medium atmosphere. Mars has a very thin atmosphere. For Venus, carbon dioxide makes up 96% of its atmosphere, followed by nitrogen, maybe 3.5%, and then trace gases make up the rest. The other stuff includes not only things like argon, which is a gas you find in planetary atmospheres, but also things like acid rain. Acid rain, which is capable of melting the surface of a spacecraft. Earth's atmosphere has its primary gas as diatomic nitrogen, 77%, pardon me. The next gas is diatomic oxygen, 21%, with a noble gas called argon making up 1%. Although it falls a little bit under the radar of 1%, because they are extremely important gases, we should mention that H2O comprises 0.4%, whereas carbon dioxide, CO2, is 0.04%. So those are trace gases indeed. Mars is more like Venus. CO2 makes up 95%, nitrogen maybe 3%, and argon maybe 2%, something like that. What's interesting about these numbers is that one of the primary gases that are produced in volcanoes is CO2. So it's natural to expect to find carbon dioxide in large quantities in a terrestrial atmosphere. One bizarre thing is that Earth is conspicuously devoid of carbon dioxide. Now, the volcanoes on Earth are pumping out the same gases that the volcanoes on Mars and Venus are pumping out, mostly CO2 and water. Yet carbon dioxide has a giant abundance, and water has a very low abundance on all of these worlds. Here's another planetary mystery for you. Diatomic oxygen. That does normally not build up on a planetary surface because diatomic oxygen is an explosive gas. Diatomic oxygen will set things on fire. That's why your blood uses it as a source of fuel. That's why we use it for rocket fuel. So it's not natural for diatomic oxygen to build up to be 1/5 of your atmospheric gas. Questions that we'd like to answer are this. Why so little CO2 on Earth? Other questions. Why so much oxygen? Here is a very interesting statistic. Do you guys see this? I'll use purple here. Do you guys see the diatomic nitrogen on Venus is only 3.5%, but the diatomic nitrogen on Earth is 77%? If you went to Venus and took a vacuum cleaner and you sucked up only the carbon dioxide on Venus, the leftover 3.5% nitrogen would be equal in volume and mass to the 77% nitrogen of Earth. In other words, Earth's atmospheric gas is only about 4% of the entire atmosphere of Venus. Venus has so much more atmosphere on Earth. The average pressure on Venus, I think is, well, it's hundreds of PSI. I think it might be hundreds of times greater than the pressure on Earth. I don't think you could stand on the surface of Venus, despite it having a local acceleration of gravity of 1g. The weight of the atmosphere would probably crush your ass like a tin can. Okay, I don't think you could actually stand up in the surface of Venus. Let's see if they have atmospheric pressure. I'd like to know the exact number here. So the temperature on Venus is roughly about 872 degrees Fahrenheit, and the average pressure is 93 bars, 93 times the pressure that you're experiencing now on Earth. So I don't think that would be very pleasant if you tried to stand up on Venus. You would literally feel the gas over your head crushing you. Like you would be reduced to a puddle of goo. And you would also melt. It would not be fun. It's funny that of all the planets in our solar system, Venus is the least hospitable. That's pretty extraordinary. By the way, do you guys know the answer to any of these questions? Why is there so much CO2 on Venus, so little on Earth? Why is there so much oxygen? You guys have any guesses as to the answers of these? Why should you care about planets? Say that?
The way our atmosphere works.
I guess that's fair. A little vague, but
our
fair.
Atmosphere traps in some and lets other ones out into space.
It actually has to do with liquid water, Tim. The water traps CO2. We have just as much CO2 as Venus does, but we've trapped it in our seafloor bed. That's the answer to one of the questions, and we'll talk about that. The other answer is also equally interesting. It turns out that the oxygen has something to do with life. So why should we care about atmospheres? Well, because you huff them and breathe them every day. You live under one. And if you're interested in life existing around other planets, you'd like to know what the conditions are for a planetary atmosphere to form. I want to start off by talking about gas. Atmospheres are made of gas. And whenever we talk about gases, we tend to want to talk about the ideal gas law. The ideal gas law is a relationship between pressure, temperature, and density. So let's look at slides 6 and 7. Wait a minute, I'm not sharing my screen with you guys. Let me try that again. Imagine that you could get in a hot air balloon and you could take a trip from the ground into outer space or something close to outer space. So you get your hot air balloon, okay? And you go on a journey where you start off at the ground, which is at sea level, and you slowly drift upwards in the atmosphere up into outer space. By the time you get to the vacuum of space, there's not supposed to be any gas left. You're in a vacuum. If we want to understand how the gas changes, we have to first just think about how gas particles work. They work like this. This is a model of an ideal gas. And in this picture, the little red BBs could represent, say, diatomic oxygen. And the little blue BBs here could represent diatomic nitrogen. And they're roughly in the right ratios of 20% to 30%. Probably someone was thinking about that when they made these drawings. The gas particles bop around with each other, and they have a number of parameters that define them. The ideal gas law relates all three. Let's take a look at that. The ideal gas law is a relationship between three variables: pressure, density, and temperature. This is the version that we use when we study physics and astronomy. In chemistry, if you took a chemistry class, you may have learned PV equals nRT. That's for weak sauce chemists. We want to use a proper physics expression for the ideal gas law, where P is the gas pressure, N is the so-called number density of the gas, K is a constant of nature called the Boltzmann constant, 1.4 times 10 to the minus 23rd joules per Kelvin. That's the Boltzmann constant. And lastly, T is the temperature of the gas. Let's talk units. What are our favorite MKS units of temperature? Hey class, tell me something about science that you've learned in the last 4 weeks so I don't have to go into the kitchen and kill myself after class because of the futility of it all. What does temperature mean? What's the units that we use?
Kelvin?
Kelvin. And do you remember the definition, Megan?
Definitions in my, I've had to use another notebook.
You had to get another notebook? Have I taken so many notes with you that you busted your notebook? Then that means you've gotten good value for your money. I have really given you lots and lots of notes. That makes me very happy. Okay. Go ahead and look up that definition. I think we could all use a memory jog. It's got something to do with this picture here. Or this little animation, I should say. What is temperature?
Isn't the definition of temperature something like the average kinetic energy of the particles in a substance?
Hell yes. Laws, yes. Okay. It's the speed of the particles. It's their kinetic energies, how fast they're moving, plus their mass. You know what I'm saying? So very good. So let's just say temperature is the kinetic energy of the particles. That's a little loose, but I'm going to be a little loose right now. Number density is the number of particles per volume, usually per cubic meter or per cubic centimeter. Because particles is a bogus concept, not a unit. It's a bogus unit. The actual units of number density are 1 / cubic meters, or in some hideous cases, when professors are being mean to their students, they like to write it as meters to the minus cube. But if you see meters to the minus cube, you should think in your mind particles per cubic centimeter. It just tells you how many gas particles are in a box, okay? So if you have a cubic meter, sometimes they use cubic centimeters as well. 5 particles in a box in a 1 meter cube box would be 5 particles per cubic centimeter. I think air at sea level has a density of 10 to the 23 particles per cubic centimeter. Let's just verify that, that I remember that correctly. Number density of air, and they'll probably just give it to me at sea level. I hit record, right? 10 to the power, sorry, I was off by a couple of, oh, here we go. Sorry. If this is 10 to the 21 cubic centimeters, air is 0.02. So 10 to the 20th, 3 times 10 to the 19 particles per cubic centimeter. That's kind of freaking nuts if you think about it, guys. So let's just talk about some averages. Averages temperature of Earth's surface, believe it or not, is 15 degrees Celsius. The number density of air in the rooms that you breathe is 3 times 10 to the 19. Oh, sorry, that was particles per cubic centimeter. Remember, class, this miniature dice, this isn't even a normal sized dice. It's a mini dice. I don't know if you can tell that. This is about a cubic centimeter. In a box this big of air, there are 3 followed by 19 zero air molecules. That's kind of fucking nuts if you think about it, right? That's like a lot of zeros to be contained in this box, and they're all bouncing around with each other. Air is not very empty. There's a lot of stuff there. In terms of cubic centimeters, did they give me that? Or sorry, cubic meters. It's 10 to the 27, 26, 25. So 10 to the 25 particles per cubic meter. How about pressure? What does pressure mean? Let's talk about pressure. I want you to imagine that I've got some air inside of a balloon. And I look at the wall of that balloon and I see that it's a thin sheet of rubber. As the particles of air bounce around, they smash into the walls of rubber and they reflect off of it. In a physics sense, pressure is a force per unit area. It's the number of force newtons distributed over a square meter or a square centimeter of your balloon wall. So this here is the wall of your container. The units of pressure in the MKS system are known as pascals. A pascal is a Newton of force per square meter. So 1 pascal is 1 Newton per meter squared. By the way, for air at sea level, is 100 kilopascals. That's the pressure of the air that's over your head right now. If you're on Venus, it would be 930 kilopascals. Or sorry, 93. Yeah, 930, that's right. Do you guys know what the imperial units of pressure are? No?
That's the bar.
That's used in meteorology. So I want to contrast 3 different units. In meteorology, they use bars. Bars are approximately 100 kilopascals. Another one that's used in planetary science a lot is an atmosphere. 1 atmosphere is approximately equal to a bar. There's slightly different definitions for an atmosphere and a bar. I don't know what they are, but it's how they average I think bars might be conducted the pressure at sea level, whereas an atmosphere might be averaged over the entire surface of Earth, something like that. So in planetary science, they use atmospheres. In meteorology, they use bars. In physics labs, they use pascals. When you go to pump up your tires at the gas station, what do they use?
PSI.
PSI. And that's pounds per square inch. The atmosphere of Earth is 14.7 PSI, pounds per inches squared. Learning about pressure is important to understand what the ideal gas law is trying to tell you. It's trying to tell you that there is a direct linear relationship between pressure, number density, and temperature. Let's learn through intuition. Always like to bust one of these out for class because they're kind of fun. They have a Java app on the ideal gas law. I think it's worth playing with for a second. Okay. You guys watching? Let's pump it up. Pump, pump. Here we go. So I now have some gas particles inside my box. You'll notice the temperature is around 300 Kelvin. That's similar to room temperature. Room temperature is 293, I think, or maybe 288 or something. And the pressure is really close to 1 atmosphere, 0.95. This is similar to what the air is doing in this room. What's going to happen if I add some heat? What are those particles going to do?
Speed up.
And what will happen to the pressure?
It should go up.
Because they'll be striking the walls of the container harder. So let's do that. So we'll heat it up, and here you can see the temperature rising, followed by a direct increase in pressure. What's happening to the number density? Is that changing?
No.
The density is fixed. Okay. Let's cool it back down with some ice. Cool down, cool down, cool down. Okay. What if I take Mr. Robot here and give it a squeeze? What's going to happen to my gas then?
Heat's going to go up, pressure's going to go up.
Yeah, the temperature will go up. Let's not say heat. Let's say the temperature will go up and the pressure will go up. Although we are providing heat in the form of work. So you're not wrong, actually, by saying that. Yeah, okay, so notice the pressure and the temperature go bonkers. Notice that when I expand it, the temperature stays the same, but the pressure drops a little bit. What's going to happen here? Let's refresh. Let's reset. Let's add a couple of different species. Let's add a pump of heavy gas, and let's add a pump of light gas. You guys will notice that at the same temperature, the lighter species, because they have the same kinetic energy, the lighter species has less mass and therefore has a higher velocity. So that's slight nuance there. What do you think would happen if I added some gravity? Hey, if I squeeze the gas with Mr. Robot, what property of the ideal gas law am I changing?
The area?
Well, the area, where does the area factor in? I see P, N, K, T. Where does the area come in?
Pressure.
I'm not directly changing
force
pressure.
over the area.
The force over the area is going up, but I'm not technically changing area. I'm changing the number density because I'm squeezing the box. If the same number of particles are in a box half as much, then the number density goes up. Do you see? Watch. If I have a box and the box is 1 cubic centimeter, if I have 5 atoms, then I've got 5 particles per cubic centimeter. If I push the particles to one part of the box and I cut it in half, I now have 5 particles for every 0.5 cubic centimeters, right? Or in other words, without changing the number of particles, I've now doubled my number density. Does that make sense? You wouldn't say the area because you're, Well, area doesn't appear in the equation. That's the first reason why. We want to be very clear about what we're saying and technical. If anything, Tim, you're changing the volume. You're not changing the area. Okay. In a way, when you add gravity to a gas, it does a similar kind of thing. Watch this. Watch the temperature and pressure. I'm going to add lots of gravity. Poof. The temperature went absolutely bonkers. That's a very interesting result. When you squeeze a gas, whether by gravity or by hand, it's going to heat up. Let's imagine that we took a hot air balloon ride and we went from the surface of Earth all the way up to outer space. And this is an important concept in atmospheric science. So how high up does the atmosphere of Earth go anyways? How high do you have to go before you're in outer space? How high does an airplane go? What's cruising altitude if you're on a plane?
20,000 feet.
30,000 feet. 30,000 feet corresponds to about maybe 10 kilometers. 10 kilometers is roughly the height of Mount Everest, okay? And it's also roughly the height at which airplanes fly. There are some jets that can go higher. So is there still atmosphere above airplane height? Yes. Go up to 50 kilometers. Do you guys remember what the altitude of the International Space Station is?
400.
I'd say by 400 you could consider yourself in outer space, except, Tim, the ISS has to do periodic corrections once a year. They have to fire rockets to account for atmospheric drag. So there are still particles up there at 400 kilometers that the ISS has to contend with. But of course, if you look at the ISS, it just looks like it's totally in outer space, right? Yeah. Not many particles, but I'd say by 300 or 400 kilometers, you can consider yourself in outer space. Now, I want you to imagine the following scenario. I can plot a number of different quantities on the x-axis here. Like, for instance, I could plot the density of air. And the density of air, I think, it's around 1.2 kilograms per cubic meter. What do you think the density of outer space is when you get to 400 kilometers? It's probably pretty damn close to 0. I wonder, students, if I took a hot air balloon from the ground all the way to the International Space Station, the density of air would obviously have to drop and go from 1 kilogram per cubic meter down to 0 kilograms per cubic meter because I'd be in outer space. I can imagine one of 3 ways the air would drop off. One way is that the air density would drop as I went to outer space in a linear fashion. So this is a linear drop-off. Another type of drop-off could be one called an exponential drop-off, in which the drop-off is great at first and then asymptotes towards 0. This is an exponential drop-off. A third option would be a logarithmic drop-off. That's where you start off not dropping by much, but then you quickly, rapidly drop off afterwards. That would be a logarithmic fall off. Now, until you perform the experiment, you don't really know which of these 3 ways the air density will drop. So before I tell you the answer, why don't you take a science guess? This is what scientists have to do. they hypothesize how the density of air will change as you go from sea level all the way up to outer space. What would you think is the most likely? If you had to just pick one.
Exponential.
Okay. Adrian says exponential. Let's see if he's right. What do you think, Adrian? Nailed it?
I think so, yes.
Yes. Okay. As we can see here, Adrian, since you're so good, by what fraction has my density of air been reduced by the time I get to airplane height? I started off at 1.2 and I ended up at 0.4 kilograms per cubic meter.
So 0.8.
I'm not asking for a subtraction. I'm asking for a reduction. What's 12 divided by 4?
Oh, 3.
So would it be fair to say that we've got 1/3 the density by the time we get to airplane height? Looks like we've got 1/12 the density by the time we get to 20 kilometers. I think that's as high as some of those super high-tech spy planes can travel. They can go up to like 20 kilometers. Certain weather balloons can go up this high before they poop out. Notice by the time you get above 40 kilometers, you're really not dealing with much at all. There's just nothing. But you know, scientists make a big deal studying the atmosphere all the way out here, even though there's hardly any gas left. What do you suppose would happen, Adrian, if we did the same experiment again, but with instead of density, what if I did pressure? Would you expect the pressure to fall in the same way, or would you expect the pressure to fall in a different way?
I feel like it falls in a different way.
Actually, because the ideal gas law relates the two, it turns out that pressure looks kind of similar. You'll see it's also an exponential drop-off for pressure. So here you are under 1 bar, 1 atmosphere of pressure on the ground. You know that we have to pressurize our cabins because by the time you get up to airplane height, humans are very intolerant to changes in pressure. Even inside of a pressurized cabin, you can feel your ears pop as you go up high in the atmosphere. It's quite unpleasant. And if you did not have that protective pressurized capsule, you would feel very strange indeed. / die. Okay, Adrian, what do you say about temperature? You just know I'm going to trick you here, right?
Yeah. I
Okay,
feel like it's gonna be. I feel like it's gonna be different from this, and it's.
and it is. It's totally insane. Temperature seems to have no relationship to either of those two, and that's what I'm here to talk to you about. First, the temperature drops as you go up to airplane height. Then the temperature weirdly goes up again. Then it drops again, and what they don't show you here is after a certain height, it actually goes up again and continues to go up all the way to space. In fact, your book has a lovely picture. This is a picture of the changes in temperature with altitude from one of my graduate texts. I wanted to show you this so I could show you guys some big boy graphs, okay? Or big girl graphs, whatever. You can see the temperature dropping up to 10 kilometers, getting higher up to 50, dropping again, and then getting higher and higher and higher all the way out to space. And why this is important is planetary scientists use these changes to define the layers of the Earth's atmosphere. And the book has a really lovely illustration of this. It's a cartoon, but it's just a beautiful cartoon that packs a lot of information in. I want to show it to you. So here, this is a famous graph in planetary science. It's known as the temperature scale height diagram. And it's kind of the basis for all of atmospheric science. It's not easy to understand. Let's see if we can draw it. So this is a famous graph. We're plotting temperature on the x-axis in degrees Celsius, this is called the temperature scale height diagram. And it's a whole thing. So we're going to start off at 15 degrees Celsius. That's the average surface temperature of Earth. I'm not going to make this too careful. We're going to drop. We're going to go up and down and all the way back up into outer space. So something like that. And there's going to be some different zones that we define as layers of our atmosphere. The bottom zone is the layer that you live in, and it's called the troposphere. The troposphere is where the vast majority of atmospheric gas is contained. Then we have this really big layer called the stratosphere, which features the famous, iconic stratospheric bump where temperature rises and falls again. That's a key thing for atmospheric scientists. Then there's a layer where the atmosphere starts to get hot, and that's called the thermosphere. It contains a layer called the ionosphere. So I'm just going to kind of put them up there. They're not exactly the same thing, but who cares? You're not going to know the difference if I tell you it is. Okay, so the thermosphere, the ionosphere are kind of the same. And then the uppermost layer are where particles can bleed out into outer space, and that's known as the exosphere. All planetary atmospheres have an exosphere where gases are leaking out into space. And these are the 4 layers of Earth's atmosphere. And we see layers like this on other planetary atmospheres as well. Although I will once again mention that, okay, I can't say that the stratosphere is unique to Earth, but the stratosphere is thought to be related to the facts that we have life on Earth and oxygen. To understand why we get these different layers and why the temperature changes so dramatically, oh my gosh, I didn't realize it was 3. I want you guys to check something out, and then I'll kind of leave my point here. Do you guys see this part of the graph where it shows us the different depths to which different types of light is penetrating? This is going to explain all the temperature changes. Believe it or not, the troposphere is not heated directly by sunlight, but is actually heated by ground light from below. Radiated infrared light from the ground is what heats up the troposphere in the form of the greenhouse effect. So it's just carbon dioxide and water absorbing radiation from below. The ground is heated by visible light. The stratosphere is heated up by ultraviolet light interacting with ozone. Ozone's an important molecule. The thermosphere is being heated by X-rays from the sun, and the exosphere is actually being heated by the solar wind more than anything. Up here at the very rarefied layers, it's the solar wind, charged particles from the sun, that are actually heating up this gas.
How far out does our magnetic field extend?
Much farther than this. Our magnetosphere extends for maybe 1,000 kilometers. That's a great question. You know, I haven't thought about that since graduate school when I took classes in plasma physics and magnetospheres. But I know it's at least got to get out here. Tim, let's look up the answer to that question, because that question interests me as well. It's a damn fine question. The reason why Tim's asking it, friends, and the reason why it matters is the magnetic field of Earth shields our atmosphere from ionizing solar radiation. So I think, Tim, what you are wondering is how much of the exosphere is exposed to, how effective is the magnetic field at blocking the solar wind, and how much of the exosphere is really exposed to that, which is a great question. So the magnetosphere of Earth, I bet has its own little web page. I've seen many diagrams like this. So I'm guessing that they'll have a little, I'm hoping they'll have a rendering of the magnetic field that has, whoa, cool music. This is a model of the Earth's magnetic field. The atmosphere is very, very close to the radius of Earth. So you can see the magnetic field of Earth, if this is done to scale, Tim, is way, way, way outside the exosphere. The problem is these magnetic fields don't block 100% of the solar wind that comes through it. Some of the charged particles can actually kind of wiggle their way through and leak through. I was really hoping that one of these graphs would have a scale on it, which would be really cool. But I guess, oh, wow. Look at this, Tim. It goes out to 65,000 kilometers. Isn't that crazy? So, Tim, a vast majority of solar wind particles not only are blocked by the solar wind, but they get sloughed off the side to our magnetotail. The magnetic field is kind of like hair blowing in the wind, the solar wind. But you'll notice that some of the solar wind ions can kind of get through and cross these boundaries. Very high energy particles can actually push by this. So it's not that the magnetic field will block every single particle. Some can leak through. Good question, though. 65,000 is much larger than I even thought it was going to be. So it's been a while since I studied that. Let's just do one little thing before we end our class today. Let's make a list of the different heating mechanisms for each layer. So the exosphere is being heated by the solar wind. The thermosphere, ionosphere is being heated by X-rays. The stratosphere is heated by interactions between UV light and ozone. And the troposphere is being heated by infrared ground radiation. And we'll pick up there next time. You guys remind me next class that I left off at the temperature scale height diagram. Okay, it's time to transition to our Mars lab. I'm trying to decide if I want to do this one by typing into, what would be the best way for me to do this? In this lab, what we're going to do is we're going to look at a map showing you the surfaces of Mars. And what I'm going to do is I might actually just keep the sheets up and then just kind of type answers into them. I think I can do that using Adobe Acrobat. That way I won't have to mess around with the cell phone camera, which sometimes has wonky results. So I hope you guys are all there hiding in the background. Now listen, if you hide from me too long, I will show you the pre-recorded lectures. So make sure somebody's interacting with me here. I am going to call up our Mars map So let's start here by putting some data in. Let's see how this goes. This is the, oh no, I don't want to add signature. Sorry, I just want to be able to type. It'd be nice if they had a better font than this piece of shit font here, but okay. What, can I? Whoa. Okay. I guess I can't change the font. So let's do our name up top, okay? Here, this is Lab 10, and this is AS1010 Summer II. Cool. We're going to be using the Mars MOLA map to answer these questions. And the Mars MOLA map shown here, just a second, guys. Okay. The Mars MOLA map is made from the Mars Orbital Laser Altimeter. It's basically a spacecraft that traveled around Mars a bunch of times, shining a laser onto the surface and measuring the reflection time and getting a very high detailed elevation resolution map. Now, because some of you guys don't know too much about the solar system, it's probably worthwhile just looking at a picture of Mars, the planet, as an overview. And you guys will see when you look at these images that the entire surface of Mars is completely red. It's red cover to cover. Now, there's a reason for Mars's red surface. It turns out to have to do with the history of Mars losing its water. This red color is actually due to rust from oxygen interacting with iron oxides in the rocky surface of the planet. So the entire surface of Mars has been rusted red. Now, why that's important and why I'm mentioning this is when you look at the topography of Mars in real color, it can be quite difficult to see what's going on because it's all so uniformly toned. So let's just look at surface of Mars. Sometimes if you look at a piece of the Martian surface, okay, well, here's like a close-up taken by, I believe, the Curiosity rover. You can see even at a local scale, you can see the red Martian dirt here, or the Martian soil, whatever you want to call it. Very dry, not a lot of erosion. I wanted to show surface of Mars, topography. I don't know. No, I don't want that. Aerial photograph. I don't know if this is going to work. I know. The Valles Marineris has a couple of nice images on Wikipedia. Yeah, that's what I'm talking about. Okay. So I want you guys to look at this photograph here. Because the surface of Mars, oh, shucks. Let's try this again. You used to be able to just get nice high resolution images without much nonsense. Whoa, 9,000 pixels. Don't mind if I do. Okay, look at this crazy photograph of the Valles Marineris. Now, one thing I'm trying to point out by showing you this photograph is if we were trying to understand the surface of Mars using true color images, yes, it would look really cool because you get a sense of just how red the entire planet is. But you'll notice that because it's all one single tone, different types of geology tend to get kind of mashed together unless you're paying really close attention. And what's cool about this, this map that we have here, this Mars MOLA map, is you'll notice the same region, by coding it in terms of elevation, all these features pop out that normally would not be very noticeable to you from an aerial photograph. Let's look at our legend to try to figure out what's going on here, just to orient ourselves. Sorry. The scale is shown up here. So you'll notice that the lowest elevations are purple or black. The highest elevations are kind of whitish or even frosty blue. So notice that this area here, the Planeta Chrysae, is lower in elevation than these highland areas. Come on. This area is even higher elevation. The peaks of the volcanoes are, of course, very high in elevation. And these planetias are much lower basins. And they're going to ask us about some features at specific longitudes. The book here is going to be using the western-based red longitudes. So prepare for them to refer to 30 degrees west as being there. Okay, let's take a look at the questions and see if we can answer them. The first question isn't a question. So we're going to go over here to question 2, and you guys are going to help me do this. You've probably noticed that the northern hemisphere of Mars is very volcanic. The southern hemisphere is heavily cratered. Based on the concept of crater density, which hemisphere do you think shows the oldest landscape? Northern or southern? What would you say, students? Is the northern or southern landscape the older surface?
It looks like the southern has more, it looks like the southern is older
Right, and how did you know that?
because of the crater density.
Excellent. That's exactly what we learned today. So let's just keep it short and sweet. No need to get crazier than necessary. Southern, okay? Inspect the Mars map provided and locate 2 basins in the southern hemisphere. The Aguirre Planitia is near longitude 40 degrees. Here's the Aguirre Planitia. The Hellas Planitia is near longitude 290 degrees. These 2 basins were probably formed by giant impacts of meteoroids. The smooth surfaces at the bottom of the 2 large craters are lava flows. Using the map, determine if you think these lava flows occurred before or after most of the heavy bombardment and cratering activity of the early solar system. So before or after? Did these lava flows here and here occur before or after the heavy bombardment?
After?
Yes. And how do you know that? What's the evidence, Adrian, to support that conclusion?
I honestly have no idea.
No, there's a reason. I disagree. There's a reason you said that. Why did you guess after that? I do not believe that was a random guess, Adrian. I believe that you had a gut reason why you said that.
Well, if there's like clear evidence of a lava flow, I assumed that there was like some kind of layer of rock there, and that would have been like obliterated by whatever made the crater.
Okay. So in other words, you're saying if there are craters in there, you'd see them, right? But how does the density of craters inside the basin compare to the density of craters up top in the highlands here?
Oh, you mean they covered the lava flow covered the craters. Is that it?
Yeah, because otherwise, Adrian, I have to imagine something really unlikely, that all the split splat happened up here, but for some reason all the splatters missed down here. Doesn't that sound very improbable to you? I would believe that this cratering is relatively uniform and would have once covered the entire surface. So I liked your, the lava flows occurred after. I agree with that. For why, we need some evidence related to things that we can directly observe and anyone else can directly observe. We'd say the density of craters in the basins is much lower than the surrounding highlands. Oh, this is really funny. If you guys want, you can type right into your PDF and email this to me. Use the map to inspect the rims of Aguirre planitia and Hellas planitia. You know, guys, the rims can sometimes tell a different story than the basins. And that's something that's worth taking a peek at here. I want to show you something. Let's play a little game called Which Crater is Older? Suppose I asked you to compare two craters and tell me which one you think is older. And the two craters I wanted you to compare were Dawes versus Huygens. Can you guys guess the older crater?
Dawes?
No, sir. I'd say Huygens. Do you know why? Andrew, I haven't picked on you enough today. Andrew, why would Huygens be older? Olivia, why would Huygens be older?
Would it have to do with how it's yellow compared to the red? With the
So yellow versus
colors
red
mean
shows
anything
us.
different or no?
You could use a little bit of that information, Andrew. You can see that this is pretty uniformly yellow, where this is yellow and red, showing us there's some higher elevation materials there. That's not too shabby, Andrew. I think you actually have a point there. But I was thinking about like the rims in particular. How does the rim of Huygens compare to the rim of Dawes?
It's bigger than Dawes.
Well, the size is one thing, but I think I should have picked two craters of equal size. That would have made this a better comparison.
The edges are kind of rougher.
Yeah, why do you think the edges are rougher on Huygens than they are in Dawes?
Things like, I think he said there was like no erosion there, but
No, Mars has wind erosion.
oh yeah, well, wind erosion causing like rock to crumble and making kind of a rougher outline.
Plus impact craters, right? You don't see any impact craters on the edge of Dawes. Maybe an old one, but it looks to me like the rim is really beat up by erosion plus cratering. Now in this question, let me clear my drawings. They ask, use the map to inspect the rim of Aguirre planitia and Hellas planitia. Look to see if the rims have more craters than the lava flows inside the rim. Look for evidence of ghost craters, which have been filled with lava. Based on the appearance of rims, which of the following historical accounts is most likely? A, the giant impacts occurred early, when most of the other impacts occurred, and excavated the large basins with their surrounding rims. The lava filled the basins much later, after most of the cratering activity was over. Or B, the giant impacts happened to occur very late, after most of the other craters had formed, and the lava fills the basins immediately. Why this could potentially be confusing is, let's take a look at how big these two impacts are. They're incredibly large. I'll show you what I'm going to do here. I'm going to zoom out a bit. And I'm going to notice that these craters are at latitude -40 or so. Let's see if we can figure out how big the Hellas planitia is. I'm going to draw an arrow from there to there. I'm going to see if I can move that arrow next. Yes. That's about the size of Hellas planitia. Let me show you how to use the Mercator projection now. How much distance you travel depends upon how high you are up. Here's the 40-degree latitude mark. I'll put one arrow at 0. Roughly, how big is the diameter of that basin there, the Hellas Planitia?
1,500 kilometers.
I'd say it's even taller than that. Look, if you follow me here, Tim, this is a curved Mercator. Anything along this line is 2,000 kilometers. So do you see?
Oh, yeah, I see.
You're looking at the top line, but you've got to be looking along 40 degrees. Our line went out there. It was clearly past 2,000. What constitutes 2,000 depends upon what latitude you're at, right? So, Tim, let's say that the impactor which created that was maybe, a good rule of thumb is that impactors will make a crater that's 10 to 100 times bigger than their diameters. So, based on that graph that I showed you earlier today, what would be the rough, well, what would you say would be the size of the impactor, and how often would you expect it to hit Earth?
Around 20 kilometers.
20, somewhere between 20 and 200 even, because it's 10 to 100 times. But yeah, that's what you said is fair. And how often would something like that strike Mars if it was pummeled by equal amounts as Earth?
Every 100 million years.
Yeah, something like that,
up
right?
to once.
Huh? Yeah. So, do you see what my point is, Tim? It's weird to imagine that both of these things happened at the end of, I can imagine something like this happening during heavy bombardment, but for two of them to strike at the end of heavy bombardment would be kind of weird, right? I would normally expect that one hit first and one hit second, and they might be separated by 100 million years. But these both have very smooth basins. What do you guys think is the best answer, A or B?
A.
Yeah. And what would be the evidence that would support this?
Well, I said that because the giant impact was older because of the edges.
Yeah, something about the rims, right? So you're saying the Hellas is older than Aguirre?
Yes.
It's a little tough. Aguirre looks pretty worn down too, right?
Yes.
I think that's the next question. In any cases, the rims show more evidence of cratering and erosion than the basins do. So let's just say that for our text answer here. We'll say the density of craters in the basins is much lower than the surrounding highlands. What's the next question ask us? It basically says, does the Hellas or Aguirre basin look older? What would you say again, Megan?
After looking at it again, I would say that our Aguirre looks older.
Yeah, I've made this mistake before too, even when teaching this course. I think, what does this stuff remind you of, Megan? Does this, learning to understand aerial photographs is a real art, but Can you think of a geological feature on Earth that you might be familiar with during the summertime that would look kind of like this from an airplane?
Forests, trees,
Pardon?
forests, trees, anything like that.
I'm
Are you
not
talking
sure.
Marsh?
I'm not sure if I would say forests or trees because these are rock formations, right? I'm sorry, did someone else said something? I want to hear what you have to say, guys.
You're talking about like a rock formation, like a jetty?
Kind of, yeah. Like, you know what I was thinking of? Now, these are little tiny hills or mountains, but I was thinking of like sand dunes or something. That looks like erosion to me. I bet at one point in Mars's history, it had liquid water flowing at its surface. Look, you can even see like a little river valley going through these craters. I wouldn't be surprised if these damn things were full of water at one point. But Megan, I agree that Aguirre looks a little bit older. Why don't we, for kicks and giggles, why don't we check to see what the radioactive dating says? The age. I thought they had an estimate of the age in Wikipedia. I'm pretty sure that the Aguirre is older. So this formed 4.1 to 3.8 billion years ago. Let's see if I can spell this right. So 4 billion years ago. And this one's 3.9 billion years ago. Actually, it's a little bit ambiguous. So this is 3.9 billion. And this is dated to 4.1 to 3.8 billion. So it looks like the research isn't actually entirely clear on this, which is kind of interesting. So Megan, we'll go with your suggestion because we don't know the actual truth. You say Aguirre's older?
Yes.
All right, then I'll go with that. But what's our evidence then?
The craters.
But in particular, the rims, right?
Yeah.
The density and erosion of Aguirre. Rims seems greater than that of Hellas. Oh, sorry. The crater density. My apologies. Most of the volcanoes on Mars look like mountains with a crater on their top. That's lame. What's our word for volcanic crater again? What do we call the opening?
Caldera.
Caldera. These are not impact craters, but are instead calderas. Use the map to estimate how many volcanoes you can identify in Mars. We'll do this one together. We're gonna say, oops, clear all drawings. The volcanoes have a couple of different types of names. Anything that's a mons we'll consider a volcano. Anything that's a patera we'll consider a volcano. Anything that's a tholus we'll consider a volcano. So if we look around here, I can see for the big guys, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Thirteen, 14, 15, 16, 17, you can even find some if you look up at the South Pole or down at the South Pole. 18, 19, 20. I don't know. We'll say close to 20. We'll say tilde 20. Can I use a tilde here? No, I can't. Okay. Now, they want us to name as many of these volcanoes as possible. Let's not do that, but let's copy the names down of the big volcanoes. Those are the ones that we see in the Tharsis Montes Plains. So the names that we're going to write down are these four here: Olympus Mons, Ascraeus Mons, Pavonis Mons, and Arcea Mons. Guys, do you know what the tallest volcano on Mars is?
Olympus Mons.
Yeah, it's the tallest volcano in the entire solar system. That's the answer to number 8.
Can you just scroll up a little bit? I just forgot to write down the last one in question 7. Thank
Sure
you.
thing. Let me know when you're all set.
I'm all set.
Okay. This question really threw me for a loop and a lump. For several years after first reading it, I meditated on it for a long time. If you were to count the craters on or near the volcanoes, would you be able to infer the age of the volcanoes relative to their surrounding plains? This really messed me up. I want you to show you guys a picture of the ones, an aerial photograph. This is from Viking 1. What are you guys seeing here?
Well, you can see like 2 craters on the top, like 2 pronounced craters.
Yeah. What do you think? Hold on, I'm just trying to get you. Yeah, here we go. So where are the craters? Can you show me?
Yeah, so if you go to the opening, to the right, there, and down there.
Right. What about these? Are these craters?
I have no idea what those are. It looks like erosion to me, but
No. What else could they be?
It looks like there could be up to maybe 5 craters in there, but also just the opening of a volcano.
Yeah. In other words, these are more likely calderas. I think, Nick, is what you're trying to say. They look, calderas have kind of the sloping edge. These are probably different epochs of eruption. What does it mean if you see 2 impact craters in the tallest volcano in Mars?
They're more recent.
Yeah. Tim, but the craters are more recent than the last eruption of lava, right?
Yeah.
What if I were to tell you that the diameters of these things, this one's about 15 kilometers and this one's about 10 kilometers? How big would the impactors have to be?
very big.
Give me a number. The rule is 10 to 100 times the diameter of your meteor is the crater you'll create.
Anywhere between 150 to 100, to...
No, no, no. You have to go the other way around. When you form an impact crater, the crater is larger than the meteoroid which strikes the ground. Do you see, Megan?
Yes.
So the meteoroid couldn't be 150 kilometers. That doesn't make any sense.
Yeah, no, I get that.
So can you revise your
150
answer?
meters.
Pardon?
150 meters.
Oh, meters, yeah. Yeah, maybe 1 kilometer to 100 meters, something like that. How often would something like that hit? Let's say it's 1 kilometer and 2 kilometers. Maybe, how long has it been since that volcano erupted?
Over 1 million years.
Yeah, well over 1 million years. So I guess in a way, we kind of can date. By the way, radioactive dating gives it, I think it's 50 million years since it erupted. But even 1 or 2 impacts is kind of enough to get a rough estimate of the age of the volcano. That's the point. Yes. Even 1 or 2 impact craters is enough to determine a rough age for the volcano. Okay, the Tharsis bulge and the Valles Marineris are thought to be caused by internal magma intrusions deep inside Mars.
I'm sorry, can you scroll back up? I didn't get all of that.
Oh, okay.
Thank you.
It's hard for me to tell, like, if I've given you enough time or not, so I sometimes assume.
Sorry, thank you.
You're welcome. All right. Inspect the area south of the Valles Marineris between longitudes 45 degrees and 100 degrees. Notice that the area is not uniformly wrinkled or cratered. A boundary seems to occur at what longitude? This is the Valles Marineris. Let's look up here. This is 30 degrees, and that's 90 degrees. So they're talking about the region kind of in these 2 boxes here. They're talking about a vertical boundary that occurs at some longitude. Do you guys see the boundary? What's the boundary that they're talking about?
You talking about the straight line that runs at the bottom of it? It's not straight. I mean, it's not parallel to lines of longitude. But.
Right. Well, what are you talking about?
How it runs almost parallel to.
Hold on. Let me see. I should allow you guys to share. Let me go to security. You should be able to draw on
You
this.
can just draw on your thing.
Yeah, just you draw. Show me what you're talking about so we can all understand. Go to annotate. Go to annotate and then check draw and do the curvy line.
So this line here runs almost parallel to line.
Wait, I don't see. Oh, there you are. Oh, no, but they're talking about a boundary in longitude. This is latitude, right? What they said in the question is inspect the area of the canyon just south between longitudes 30 and 100 degrees. Can you see a boundary at some longitude? The line that you drew, Tim, is a horizontal line which follows lines of latitude. Does that mean I've lost you or?
Yeah.
Oh, shoot. Can nobody out there on
Well,
the
I mean,
team?
I know the difference between latitude and longitude. I don't understand what they're asking.
Is it
They're
the-
asking that if you look south of the canyon, the area that you're looking at, which I've drawn a red box around, is not uniformly wrinkled and cratered, but has a boundary at some longitude. Can you tell me what the boundary between two different planes are? Yes, the Nectaris fossae. Good. That's a boundary between two. Was that you, Tim, that made that black line?
Yeah.
Okay, cool. What longitude does that occur at? Let's travel up here. Oh, okay, here. So it looks like that longitude is pretty close to, let's use the straight line here. What's that tick mark represent? Can you tell me the longitude? I'll give you guys some hints. Huh?
58?
Yeah. 57, 58. I'll give that to you. Is the younger surface to the east or west of the boundary? So what's the younger surface here? This is east. This is west.
It looks like the west.
Yeah, the west is the younger surface. I agree with that. There's just fewer craters there than there are here. Good job. Oops, sorry. I did not mean to do that. Look at the smooth plain called Tharsis Montes. Does crater density suggest that Tharsis Montes is older, younger, or the same age as the region south of the Valles Marineris? In other words, what if you compared all this stuff to this area over here? If it's this versus this, is the volcanic area younger, older, or the same age?
Younger?
Yeah, you can see that it's much smoother the closer. The point they're trying to make is the closer you get to the volcanoes, the closer you get to the lava repaving and the younger the surface is. Okay. Along the north rim of Valles Marineris is a place called the Candor Chasma Rim. It's located in the canyon, and it's near coordinates longitude 70 through 75, latitudes -3 through -8. I really want to show you a picture of what they're talking about because it's pretty cool. Now, the Candor Chasma Rim is hard to see on this map because it's like too busy. This structure here is what they're talking about. That's the Candor Chasma. There's a really sick picture of this on Wikipedia that I think is worth looking at. In fact, I think it's right at the Valles Marineris here. Where is that? Whoa. That was picture of the year in 2006. That's really cool. Look at this nuttiness here. Oh, geez. Oh, here we go. It's a super high resolution image. Sorry. This is probably like 9,000 pixels or something stupid. Wow, that's so slow. It's probably not going to be fun for this data to travel from my computer to your computer over the internet. But looking at the low resolution picture seems uncouth.
Do you think that's how they wait for them at NASA?
Yeah, probably the bit rate is pretty small. Like, imagine trying to log into your Wi-Fi hotspot on Mars. It's not so easy, right? In fact, Tim, it's probably very similar to that. I know this photograph is so badass, which is why I'm kind of like making you guys suffer for it. This is a true color image. What type of geology is at work here, students?
Erosion?
Yeah, probably. I have to admit, this is a little more, whoa. All right, this is just ridiculous. Let me type, hold on a second. Sorry, I'm just. I don't know about you guys, but that sure looks like water erosion to me, right? All that craziness looks like sand dunes there, right? Is this a young or an old geological surface feature, Tim?
Old?
Well, what's the #1 indicator of planetary age?
Impact craters?
So,
I guess I'm saying that because I know it's been a long time since there was liquid water on the surface of Mars.
right, but there's a long time and then there's a long, long time. You know what I mean? It depends if you're talking about like geological timescales versus astronomical timescales. I want to zoom in without zooming all the way in, but I guess that's kind of hard to do. Oh, okay, hold on, here we go. This is just too freaking crazy here. Tim, I see craters above, right?
Yep.
Let me go back to the other one. I can see craters all up here. And I can see craters here. If this is an old surface, why don't I see any craters in there?
True.
You know what I mean? Like otherwise
It has to be younger.
It has to be wicked young. Now, you're probably thinking old in terms of a human being. Yeah, there was no water on Mars 100 years ago. But there could have been water on Mars 100 million years ago, right? But those craters, they've been forming for billions of years. You see what I mean? It's kind of like a telescoping timescale there. So I think what you were trying to say is, yeah, it makes sense for you to say there wasn't water on Mars 10 years ago, but this even if this is 100 million years old, this is still a pretty young surface, right? In fact, I bet there was water flowing here millions of years ago. Mars, if you could just go back a million years when humans were first forming, Mars probably was a much wetter planet than it is today. It's been dying off. Which is one of the reasons why it's so exciting. The Perseverance rover, by the way, guys, which just headed to Mars, it's planning on dropping into, I'll tell you the name of the crater in 1 second here. Let me just zoom out a little bit. The crater that it's headed for is up here somewhere. Does anyone remember the name of that crater? Oh, sorry, I'm having trouble grabbing this stuff for some reason. I think it's heading somewhere around here. The videos of this, the Perseverance. Sorry. The Jezero crater in the Insidus Basin. Okay. So I had the right area, but I couldn't remember the Jezero crater. That's what I was forgetting. So that means it's headed right up here somewhere. Can you guys guess, why do you think they chose this? Why do you think they chose this as a landing site for the rover? Why there versus anywhere? There are so many cool places you could go on Mars. Why go to that place?
Well, I don't see any volcanoes.
Yeah, I guess they weren't interested in the volcanoes. What are they looking for? Why go there? Why not go here or here or here? Why?
Didn't like the water that used to be there.
Yeah, where do you find the greatest amount of life on Earth?
Where water is.
But not just where water is, but where it meets the land, near the seashore, right?
Could they not go to the ice caps?
They could have. They got to choose, but think about it, Nick. Obviously, it would be fucking amazing to see the ice caps. Have you ever heard of, there's a chasm, the Chasma Boreal in the ice caps? They have these high-resolution images, and I got to show this to you, because part of the reason for this lab is just to show you guys some sick photos of Mars, stuff that you maybe never took the time to look up or didn't even think about. Let me show you how beautiful the Chasma Boreal looks. It's probably one of the most beautiful places on Mars. And that's frozen carbon dioxide that condenses and shrinks over the course of the year. Do you bet I'd want to see a rover traveling around the Chasma Boreal, Nick? Hell yes. But Nick, we only had 1 or 2 rovers, and let's take a look at where they've been sending them. They haven't sent them to the Chasma Boreal. If you look here, they show you the landing sites of some of the other rovers. Look, that was the Viking 1 landing site there. That was the Pathfinder landing site. Curiosity is down here in Gale Crater. Where do you see them heading? Where do you see them sending all their missions if they've only got 1 or 2 to send? They're taking those bastards to the seashore, and they're looking for microscopic single-celled protoplankton or something that might be buried in some soil underneath this softer clay, you know, where that might have once had water a million years ago. Their bet, Nick, is that it would be totally cool, first and foremost, to find out if life could have got a foothold there. That's going to have profound consequences because it means life is not unique. It means that Jesus didn't wave his magic wand in the oceans and up came the fishes. It means that life is a natural consequence of the chemistry that forms at the surface of the planets. And that would be a pretty cool thing to discover, right? But yes,
if we found that life existed on 2 planets in our solar system, how much would that increase the likelihood in other solar systems?
I don't have a number, but it would be a tremendous probabilistic increase because it would mean that whatever complex chemical reactions took place to form life, it would mean that, you know, one idea is that it's just a freak accident, that we just got really lucky. Another idea is that if you put all of these ingredients into a laboratory the size of a planet and you cook them for billions of years, then this is going to happen. But right now it's hard for us to say either way because we only have 1 known planet that has life. And up to recently, we've only had 8 planets that we could study in detail. And we still don't know that much about the other 8 planets, if you think about it. We're still trying to figure out Mars. So to find it there would mean that there was a much greater probability that we'd find life out there. We suspect there is, but it's one thing to suspect it. It's another thing to have physical evidence, right? That's a more compelling argument. So yeah, it would be a crazy game changer. It would mean that the probability of aliens goes up big time. And that would make a big sci-fi nerd like me very happy. All right, let's just knock out a couple more of these questions and then we'll stop. We're almost done. So, does this area suggest the canyon is younger or older than the plains to the north? What did we decide there?
Younger.
Younger. Okay. Now we look at the rims of Valles Marineris. Is there anything along the north or south rim that shows evidence of flowing water on Mars? Duh. You can see some. Now, they call these things alluvial fans, okay? That was the key word I wanted to teach you guys today. You see these things on Earth, alluvial fans, where water erosion, sorry, I spelled that wrong, kind of creates structures that look like this. Here's a telltale sign of water erosion, right? Streaming through this channel here. And if you look at that, that Mars map, you can see things that look just, oh shoot. Sorry, I've got too many damn things going on here. If you guys look in the interior of the Chasma Boreal, you can see stuff that looks almost identical to that. So clearly there's evidence of flowing water all throughout here. That's what creates this feature. Today it's gone, and that's because the atmospheric pressure is too low. Okay, sorry, let's get rid of that guy. And let's get back to this guy. I think I just want to do one more, okay. Suppose we look at the crater density inside Valles Marineris, and we try to choose one of the following historical accounts. The canyon forms before the surrounding plains, and the lava flows which made up the plains did not reach the canyon. The canyon was cut into rock by a river of lava from nearby volcanoes. The canyon forms a boundary between two plains of different ages, or the plains formed first and at one time covered the area. Valles Marineris forms later from an unknown cause. None of those options are great, but which do you think is the least sucky?
D.
Yeah, I agree. The idea is that unlike our Grand Canyon, which formed entirely from water erosion, we believe that Valles Marineris was too big a feature to form just from water erosion, but started off as tectonic in origin and had some kind of deep fissure or crack in the planet that then got filled in by water erosion. So you should know that the Valles Marineris is more complex than the Grand Canyon. This will be our final question here. Look at the area around the volcano Arcia Mons. Use a magnified image to locate several ridges or channels on the side of Arcia Mons. Make sure the channels were made by the volcano. Follow the structures to see if they extend out onto the surrounding plains at their base. Look for any evidence that Arcia Mons has been covered by some other geological development. Choose one of the following accounts. The volcano formed first and was buried later by a lava flow from another volcano, or the volcano formed the plains from its own lava flow and the plains have the same age. It's kind of difficult to understand what they're talking about just by looking at a picture of Arcia Mons. Arcia Mons, or just by looking at this map rather, Arcia Mons is the lowest of the three really tall volcanoes. And I think the channel that they're referring to, you can just barely see it, is this channel there. And they're showing this kind of material that's coming off of the volcano here. You really get a better sense of what's going on if you look at a high resolution image. Arcia Mons. A nice black and white photograph. Here we go. From the Themis spacecraft, which is pretty cool. Okay, guys, talk to me. Look at this. Look how detailed this is. What the hell is all that crazy shit? Here's your main caldera. Notice when you look at very fine details, you can see even a few craters all scattered throughout that, right? What about all this stuff? What do you think? What kind of geology caused that channel?
Water erosion?
Megan, is that you, Megan?
Yeah, that's me.
That's what I thought too the first time I looked at this. The first time I looked at it, French fries, I thought we were talking about water erosion. And then I realized that that's not what it was, because there were no channels connecting this stuff. I thought it was water erosion too, but it's not. What are these things? What is all this stuff?
Are those calderas?
Exactly. So what does that imply then?
Lava?
Yeah, this is what you would call a side vent, where volcanoes just blast out of the side of this thing. They have a name for them in planetary geology. I think they call these things collapsed lava tubes. And you not only see them on Mars, but you can see them on the moon as well. They're places where lava just kind of, there's no wind or water erosion on Mars, but where lava just creates these big depressions as volcanic material is blasted out. Let's see if there are other examples of collapsed lava tubes. Yeah. Here you can see they almost look like chains of craters, but they're actually, what happens is after an eruption, the lava that's cooled sits on top of the magma chamber like a Fabergé egg, and the weight of the rock then just collapses the empty cavity. And if you look at our Sea Amons, not only can you see collapsed lava tubes here and here and here, but you can also see them up at the top, like over here. So that suggests that probably, if we had to answer one of those questions, well, what would you guys say?
Would it be B?
That's what I would choose, B. And all I'm going to have you write for why do you think so, just for fun, collapsed lava tubes. Okay. Okay, I think you've done enough exploring the surface of Mars with me today. You guys can just upload that PDF, save it with your annotations, and upload it to my grading sheet, okay?
Can you please just pull up 13 and 14 really fast for me, please?
Absolutely.
Thank you.
Where are we here? 13 and 14?
Yep.
Sorry, I might have gone a little quick there. I was trying to be speedy.
And number 16, I just didn't finish writing, and then I'm all set.
Okay. Oh, number, which number?
Number 16. Thank you. All done.
All right, cool.
Perfect.
All right. So now that we're all set, please submit those to me. We've got one more class left together, and then we'll be done with this course, okay? Any questions or comments for me before we, hold on, I saw a chat come in here, so let me, oh, see you, Megan, that's fine. Okay, guys, one class left and then we're done. I'll see you guys on Wednesday.
Thank you so much.
Wait, before you guys go, all work, I want to get it in by like Thursday so I can finish grading and be done. You guys hear that?
Yes.
That's very reasonable, right? We've been doing it all together. You hear that, Destiny and everyone else? I want that work in by like Thursday so I can grade it all for Friday. Okay. I'll see you guys later.
I just have one question before.
Oh, yeah.
But it doesn't pertain to anybody else. So if you guys want to head out, that's fine.
Okay, sure.
But I just have a question. So on Wednesday, I will actually be going to New Hampshire in like the afternoon. So it was a vacation that I planned prior to taking the class, so I wasn't planning accordingly. But would it be okay if I watched like the pre-recorded lectures and then just submitted the work and took notes that way to you, and just so I could get the work in at least?
Yep.
Okay.
So do you want the link for that?
I think I found them actually, unless you want to send them to me, but I think I looked up your I did look up your YouTube and I found the summer one.
Did I post the last? I'm wondering if I posted the last lecture, because what would have been my motivation to do it? Wait, let me just check.
Okay.
So wait, it would be then.
I think
homework 10 and lecture 11, right?
Yeah. And,
okay.
Yeah.
No, actually, maybe I did post it. I must have posted it. Okay. So if you found homework 10, lecture 11, then yes.
Okay.
I don't think we did a lab that day, so you can just get the homework done, okay?
AS Summer 1. It was the 10-10 class, obviously, right?
Yeah.
Yeah, homework 9, lecture 11. Is that? No.
No. Oh, yeah,
Um,
sorry. What did we do today?
We did. We did
Homework.
homework 8, lecture 10. So yeah, homework 9, lecture 11.
Okay.
So I have it pulled up.
Okay. So homework 9, lecture 11, right?
Yeah. Yep.
All right.
I'm gonna try
Okay.
to join in the morning just so I can at least have some part, but
Yeah, exactly.
Okay.
Since it's the last day, if you want to do the office hours with us and then bounce,
Yeah.
that's fine. Okay.
okay, that sounds
However
good.
you guys want to do it.
Okay.
So great hanging, which is as always, and I'll see you on Wednesday. Okay.
All right. Sounds good.
Bye.